I would like to welcome our guests, our tutors from MathWorks, Raymond, Norris, and Shubo Chakrabarti. And I would like to say that we are very, very happy and very grateful for them to come all along from the US and Germany to give you this course on parallel MATLAB. I would also like to welcome you, our participants. We are very happy to see so many people on site who have come to IT for Innovations. And we also welcome the online participants. This means that we are going hybrid, so we would like to ask you for a bit of patience with if there are technical problems, which we do not foresee, but it might happen. And I pass the speech to Raymond, so thank you.
Thank you. Good. All right. Well, thank you, everyone. I appreciate it. And, thank you for the invitation to come here. It's my first time ever been to the Czech Republic. It's a beautiful country, beautiful land here. So I appreciate the invitation. So thank you. Clearly, you can tell from my accent, I'm not from here. I'm from the United States. I'm on the East Coast, just outside of Boston, near New York City, for anyone who's been to the United States. So it's been a long trip. But again, very enjoyable. I'm also here with Shubo, my colleague. We have MathWorkers online, and we also have local representation from Humasoft. So thank you for coming and joining us today as well. So, all right. So let me give an overview of what I'd like to accomplish for today. Right. This is a hands-on workshop. I'm going to encourage everyone to follow along with what we're doing. For some of you, maybe you're less familiar with MATLAB, or maybe you have more experience with parallel computing. We have many people here who can help and aid you. So if you have any questions, please, feel free to, either put things into the chat, raise your hand, and so forth. Okay. The morning session is all about the MATLAB parallel language. So let me just raise a hand. How many people, is everyone a MATLAB programmer? A couple of people. Okay. Okay. Is there anyone, this is perhaps one of their first times using MATLAB? Okay, good. Yeah. All right. What about parallel computing? Has anyone written a parallel for loop? Any experience? Oh, fantastic. Excellent. All right, good. So we're going to spend some time talking about what a parallel pool is, a parallel for loop, talk about some of the parallel constructs, and so forth. So it's all about the MATLAB parallel language this morning. We'll take a break about 10:30, and we'll go until 10:45 for a 15-minute break. And then I would expect that we will wrap up by 11:30, 12 o'clock at the latest. Okay, 12 o'clock to 1 o'clock, we'll have a lunch. I'm not sure where, but we'll have some lunch. And then from 1 o'clock until 4 o'clock, we'll have part 2 of our hands-on workshop. The second part of the workshop is all about how to write your code to scale on the Carolina cluster. So raise your hands. How many people have done any work, regardless of MATLAB, on Carolina? Has anyone used Carolina before? A couple of people up here. Okay, a little bit here, a little bit there. Okay, all right, fine. Not a worry, because I'm going to explain to you how you can connect to Carolina, how you can run MATLAB on Carolina, and how you'll be able to run MATLAB jobs on Carolina. Okay, so the morning is all about the parallel language. The afternoon is all about how we can run our jobs on Carolina. And my goal is to be completed by 4 o'clock. We'll take another 15-minute break in the afternoon as well, about from 2:30 to 2:45. So sound good? Okay. I ask a lot of questions. So to encourage answers, I have gimmicks. I have things I like to give away. I will hand it to you. I won't throw these at you. Don't worry. But I've got a pen. I've got a screwdriver. I've got a deck of cards. I don't know if people like to play cards, but there you are. And I have a little, I need to get a mobile phone stand. So these are very attractive. These are very in high demand. So I encourage you to ask questions yourself. Again, raise your hand, but occasionally I'll ask questions and just to see how if folks are following along. And if you're more comfortable, feel free to put your questions in the Zoom chat. And the staff from MathWorks and Humasoft will either answer the question or raise it to my attention. So, all right, with that said, why don't we get going? So, as I've already mentioned, I'd encourage folks to put things onto the chat. When you do put things in chat, please announce it to everyone so that everyone sees the questions. Quite honestly, the questions that you have are probably questions everyone else has as well. So everyone will see the answers. Okay. So the morning session, we're going to be talking about running part 1 using just the parallel computing toolbox, and we're going to be using an online classroom that we call MATLAB Online. Some of you may have some experience using MATLAB Online. This is a slightly different version that we're going to be using today. Today's version has access to several additional cores, plus it also has access to a GPU. So we'll talk a little about GPUs and so forth, okay? All right, let's get started. So I think the first question that we have to ask is, why are we here, right? So we all seem to understand something about MATLAB, but there's a problem that we're trying to solve, and that is that either the code that you're running is taking too long to run, the code that you're running runs out of memory, or perhaps you need to be able to take your code and offload it into a supercomputer or another system to free up the resources on your local machine. And that's really what it comes down to, and that's what we want to talk about today, okay? So let's give some basic, simple examples. Imagine that you have 1 million images that you want to process, right? Maybe it's images, sound waves, whatever the case is, right? And in order to speed up that code, you'd like to take your MATLAB for loop and parallelize that loop so that way we could process those 1 million images in a much faster period of time, right? Okay, so that honestly is probably the largest and most common scenario where MATLAB users are trying to understand, how can we take our MATLAB code and run it faster? Instead of 1 million images, imagine I've got one image, right? One medical image, you know, and it's too large to be able to load into my MATLAB workspace. And so what I need to do instead is take pieces of that image and dole it out to multiple MATLAB instances, stitch all that data together, and then operate it as if it were a single variable. But in fact, it's a distributed array. So this is what happens when we run out of memory, right? So if on your machine you have 16 gigs of RAM, Carolina, et cetera, have access to gigabytes and terabytes of RAM. So it's, you know, much larger problems that can be solved. And then the third scenario is, you know, perhaps your code can't be parallelized, right? So we have what's referred to as cascading algorithms. That's a piece of code that depends on previous iterations, right? So maybe A of I is dependent on A of I minus 1 and so forth, right? So you'll never be able to parallelize that code. But because it takes too much time on your machine, you'd like to be able to take that code and offload it and place it onto Carolina, where you have significantly more cores, more compute, and allowing you to do more desktop or engineering on your desktop machine. I think those are the three basic scenarios, right? You want to speed up your code, you want to deal with out-of-memory issues, or sometimes simply use your desktop for other development work and do your doing your prototyping here, and instead run your compute in the cloud, Carolina. Right? All right, so that's why we're here today, right? We want to talk about how we're going to leverage the multiple cores on your local machine, and then how we can use the MATLAB API to run jobs onto the cluster. All right, so I think before we talk about parallelization, we should sort of level set and just sort of understand what are some of the things that we can do today before we even start parallelizing our code that can make significant improvements to your MATLAB code. If your code can be sped up by an order of magnitude, maybe 5 times, 10 times faster, before we start running things on the cluster, we want to take advantage of what we can use locally. So there are some basic MATLAB development tools that we can use today. Okay, get ready. Here's the first question. All right, so what are some of the MATLAB development tools that you could use to identify how long it takes to run your code, or how you can make improvements to your code? Any ideas, any suggestions? And I'm also talking to the folks online. Yes. Tick and talk. Okay, so when we talk about code running it takes too long, the first question I have is, how are you measuring your time? Okay, so I can think of probably 3 ways to measure time, and TikTok is probably by far the most common, right? The least common might be, well, actually, you might be surprised. Probably the most common is they just look at their watch and they say, I don't know, it's been running for a while, it takes too long, and I need it to run faster. And that's a harder problem to figure out because, well, we have to set expectations, right? So then we say, okay, let's run TikTok, right? So TikTok is a MATLAB function that you can time how long it's going to take to run your code. You seem like a card dealer, so I'm going to give you a deck of cards here. So, excited about that. Okay, well, there you are. You're welcome. So, what we want to be able to do is get actually a more realistic expectation of how long it takes to run your code. So the third is through the MATLAB profiler. the MATLAB profiler allows you to instrument your MATLAB code and figure out how long it's taking to run your code. Because I'm going to give you the following scenario. Let's say your code takes 10 hours to run, okay? And you'd like it to run 10 times faster, so you'd like it to run in 1 hour. Okay, but now what if I told you that we spend 2 hours, 2 to 3 hours doing pre-processing? We have to clean your data, et cetera, right? Okay, there's maybe no way that we can parallelize that, right? That's some serial work. We're reading from a database, we're cleaning up our missing data, et cetera. And now I have a for loop, and that for loop takes 5 hours to run, okay? And then once the for loop is finished running, now I'm going to do some post-processing, right? I'm going to generate, the compute is done, and now I want to do some post-analysis. I want to publish my paper, et cetera, and so forth. And that takes a couple of hours to run as well, just hypothetically, right? So you told me that it takes 10 hours to run, but in fact, if we really think about it, that for loop is the one that we could probably parallelize. That's our hope, right? So we can get that, maybe ideally, that 5 hours down to 0. Like let's just, in a utopian scenario, we can get 5 hours down to 0. So we went from 10 hours to 5 hours, because the 5 hours is the pre and the post processing. So I can throw 1,000 computers at this job, and the best I can get is a 2 times speed improvement, right? So we have to set expectations. Now, what if instead we say, okay, we're going to disregard the pre-processing and the post-processing. We're just going to focus on the for loop. If we can drive that for loop from 5 hours to 45 minutes, or let's say 1 hour, because my math actually isn't terribly good, I can get a 5 times speed improvement. Okay, so now I can start thinking about, it still doesn't make sense to throw 10 or 20 computers at it, but maybe realistically, I can get your code to run 5 times faster, right? So if we look at the entire body of code, it takes 10 hours, and maybe I can get it down to 5 hours, 2 times speed improvement. But if we just focus on the piece of code that really we can speed up, I can get it maybe from 5 hours to like half an hour, 45 minutes, and so forth. That's a much more realistic way of thinking about it, right? So anytime I'm working with users, the first thing I'm going to ask is, how long does it take? How long do you want it to take? And how do you come to the assessment that it's taking that much time? We have to set expectations. Okay, so MATLAB Profiler is one of the first things that we can do in order to be able to time our code. Now, for those, we're going to be using MATLAB Online, which unfortunately, I can't find the MATLAB Profiler, but I'm going to just highlight where it is in your MATLAB. Okay, so the profiler is one of our development tools that we can use, and it is this is MATLAB Online. Sorry, I just jump over to. Okay, so the analyze code is the MATLAB profiler. Now you'll see this in your MATLAB desktop. We're not going to be using the desktop this morning, but the code analyzer will not only tell you how much time you're spending in each block of code, but it'll also show you where you're not running some code, what we call dead code, okay? So dead code is code that you probably could remove because over time, it's become stale, and in fact, that code never gets run anymore. But the focus right now is talking about determining how long it takes to run the code. So there are different coding techniques that we can use in MATLAB. And so the profiler may identify that a certain body of code is taking a certain amount of time and how we can speed that up, right? So if I run the profiler on a block of code, then I can see that a certain amount of time is being taken to run. And then I can think about how I can speed up that code. And we're going to talk about some techniques in a moment. But the reason that this is important is for the following. I have two for loops. One for loop has 10 iterations for I equals 1 to 10. A second for loop has a million iterations for I equals 1 to a million. So my question to you is, if you could only parallelize one of those for loops, the one that only has 10 iterations or the one that has a million iterations, which one would you spend time trying to parallelize? And for this, I have a screwdriver. More iterations, okay? Memory. Okay, so the answer provided a moment ago is that I would spend parallelizing the one that has 1,000,000 iterations, right? Assuming it can fit into memory. Okay, now what I'm going to tell you is that the 10 iterations takes 10 days to run, and the 1,000,000 iterations takes half a minute to run, right? So in fact, the number of iterations has nothing to do necessarily with how long it takes to run your code. And as you're going to see today, there's a certain amount of overhead associated with running jobs on other processes that we call workers, right? So we want to understand how much time does it take to send data and instructions to these workers. Okay, that's a term I'll define a little bit later. And it's possible, in fact, that we spend more time sending instructions and data, even though there's 1,000,000 iterations to run, than it would be for just 10 iterations that maybe takes 10 days to run, right? So I'm willing to take the overhead of however long it takes to parallelize the code because I want to get those 10 days down to half an hour, okay? All right, so what the profiler tells us is that, yes, we're running, 1,000,000 iterations here, but in fact, it's taking less than 1 second to run. And so would I necessarily parallelize this for loop? Probably not. It's just probably not necessarily worth the time. But there are other techniques that we can use. And so perhaps we can vectorize our code, right? So for some of you who've been using MATLAB for a while, you understand the notion of vectorization is compressing the code so that we work on matrices rather than using for loops to iterate through one index at a time, okay? So I'm not suggesting that we don't necessarily address some of the deficiencies in the code, but it doesn't necessarily mean that we have to parallelize everything first, okay? In this case here, it's just a simple example of vectorizing our code. Okay, so I know everyone writes fantastic code. There's no bugs in your code. Perhaps I'm the only one who writes buggy code, but the code analyzer is another development tool that we have. And for those who use Microsoft Word, and perhaps you've had typos in your document, and you'll see a little squiggly, and it tries to identify, well, here's a recommendation of spelling it this way. Well, the MATLAB code analyzer actually works in a very similar way as well, right? These are hints that MATLAB recommends using to help make improvements to your code, right? Now, it's not necessarily going to get from 10 hours down to 1 minute, but if you don't address some of your memory concerns, you can actually get some good speed improvements if we do what? One of the things that MATLAB is known for is being able to dynamically grow its matrices. So one way that we can combat how long it takes to keep growing our matrices is what? Starts with the letter V. Anyone, what's the MATLAB term that we use? I'm sorry, not V. V is vectorized. Starts with the letter P. Yes, pre-allocation. Okay, I'm sure you have a phone. Well, I'll tell you what. Perhaps you have. I mean, it could be for you or your kids, or if you don't, I mean, I don't know, but yeah, glasses? Yeah, glasses. Okay, there you are. All right. Right. So pre-allocation, there you go. Thank you. So pre-allocation is the ability of taking a matrix and allocating all the memory MATLAB needs up front. So that way, all we're doing is, rather than dynamically growing our matrix, is that we are substituting, okay? And so if we can ask for all of the memory up front, right? So all, 1,000,000 by 10,000,000 matrix, and then our assignments just become reassignments rather than dynamically growing it. And so the code analyzer can help show us where we can make improvements to this, right? So let's take a look at the code here. So we have a for loop where we are continuously growing the matrix, and then down below we'll show where we can. Well, actually, in this case here, we're showing that it can't be pre-allocated. Okay, sorry, we'll go back. Okay, so by using initialization matrices like or functions like zeros, nan, ones, etc., rand, we can allocate X all at once. And then when we're on line 4, we're simply just doing substitution. So The one I particularly will use is NaN because, in fact, values could be 1, 0, or random numbers, but typically NaN really tells me that if I haven't assigned a value, then it's easier to determine that if the value still is NaN. So, all right. So there's a lot of different programming tips and tricks. Another one is perhaps even writing your own C code and then using the MEX interface. The MEX interface is a thin layer between MATLAB and a C or Fortran library or DLL, a shared library. And it can do one of two things. Either it provides a way of speeding up your code because we're writing it in C code, or it provides a layer between MATLAB and a third-party library like a database or some code that perhaps you've written and so forth. So you can hand code your MEX files, or you can use the MATLAB coder, which you should have access to. And the MATLAB coder will automatically generate MEX files for you. This tends to be a more advanced feature, but certainly an option. All the things that I've talked about are different tips and tricks that you can use. And we can have an entire seminar on this. I'm not really going to spend much more time on these things, but these are things that you should be thinking about before we start looking at parallelization, and certainly before we start running jobs on Carolina. So any questions on this before we go on into the meat of today? Shubo, how are we doing online? Any questions, anything being prompted? I'm sure they were all right. Okay, so when we talk about parallelization, it's important to understand or make the distinction between implicit multi-threading and explicit multi-parallelization, okay? And what we're going to focus on is explicit parallelization, right? So explicit meaning that you are going to do something to your code that explicitly says, MATLAB, I want you to parallelize this code, right? So just like the for loop I was mentioning earlier, when we have a for loop, we don't necessarily know that you would want to parallelize that because maybe there's not enough work being done. So you have to opt in to parallelize that code, okay? But before we talk about that, there's also implicit parallelization. And implicit parallelization is parallelization that happens without you needing to do anything, because MATLAB, like a lot of other fourth generation languages, other scripting languages, are built on math routines that we all use. We're all using the same BLAS and LAPACK routines, and MATLAB layers on top of that as an abstraction. And so, for instance, if I were to call the FFT of a matrix, MATLAB is implicitly threading that those instructions to multiple cores on your machine without you needing to do anything else. Shubo, you have a question online? Okay. Okay. So we're talking about a C compiler, or are we talking about the MATLAB compiler? Yeah. Okay. So the MATLAB compiler really is just creates what we a thin layer of code that sits on our MVM, the MATLAB virtual machine. So anything that MATLAB can do, the compiler, when it's running code, is actually just running the same code. Years ago, now that's a little different than MATLAB coder, and I'll talk about that in a second. But when you use the MEX interface, many years ago, we were actually generating C code. Now it's just a wrapper to the MVM. So it's actually calling the exact same code. If you can vectorize your code, then you can compile that, and that works perfectly fine. So, all right, good, excellent. All right, so let's continue. As I mentioned, MATLAB has a significant number of built-in functions that are already highly optimized for the cores that are on your machine. And in fact, one of the dichotomies that we run into is that you are sometimes going to find that you are combating multi-threading with multi-processing, okay? So let me just explain. There is certainly a difference between threading and processes. Threads are lightweight processes that are attached to a single main process. They share the same memory, they share the same instruction sets, and so forth. Processes are spawned from other processes and have their own memory space and so forth. And in fact, these processes can exist or be launched onto different nodes versus threads all have to exist on the same node and so forth. So you could imagine that if I've got my laptop that has 4 or 8 cores and a certain amount of memory, and I run my code using implicit multi-threading, it's using 4 cores. If I then want to instead enable multi-parallelization, multi-processing, we reduce the multi-threading and we replace it with multi-processing. And sometimes they end up just canceling each other out. Where you're truly going to see the benefit is when you start moving to Carolina, where you have multiple nodes. That's going to allow you to do multi-threading across a single node and multi-processing across multiple nodes. We'll talk more about that in the afternoon session. So, okay. All right. So MATLAB language itself, until about a year ago, was always single-threaded. Now, let me explain what I mean by that. The MATLAB desktop is a Java-based desktop, and that does support multiprocessing. That's fine, or multi-threading. And MATLAB is built on math libraries that are multi-threaded. But the MATLAB language itself, right? If I run a for loop while it's running, I can't do anything else. The reason I say until about a year ago is just a year ago, we introduced this notion of a background pool. And the background pool is the first time that we've provided a user with the ability to launch a process off of the MATLAB main executable thread and run while other MATLAB code is running, okay? We're not going to talk about background pools much today, but I'm happy to have a further discussion. Where a background pool is really advantageous is through MATLAB apps. So when a MATLAB app is running, there's no ability to be able to refresh or update the figure or the windows while something is running. But now MATLAB provides the ability to launch a background process running the compute while still refreshing the MATLAB app itself. So it's really a game changer, and it's really the first step in a lot of what we're going to be doing for parallelization for the users. Okay, so let's move on to this explicit parallelization, because that's really what we're going to be talking about today. And in order to do this, the first thing that we have to do is we have to have a pool of processes called workers. A worker is a headless MATLAB process. And when I say headless, what I'm saying is that when we start up a pool of these processes, we're not going to see 4 or 5 desktops all popping up. There's only going to be one desktop that's running, and that's your MATLAB client. But in addition to the client, we're now providing a command called parpool, and parpool allows you to start up these pool of processes. In the morning session, this pool of processes are going to be on your local machine, and we're going to use that term local several times. When we're on the cluster this afternoon, I'll show you how you could run a pool of these processes across multiple nodes, and that's really the game changer here. The nodes or machines on Carolina have 128 cores, significantly more than the laptops that we have today, right? Some of us have 2, 4, maybe 8 or 16 cores, but nothing compares to the amount of cores that Carolina has. Okay, so in order to run any parallel constructs, things I'll talk about later, like par4 and so forth, you need to have a pool of processes that are running, and those processes are called workers, okay? All right, so with that, I think we should jump into our first example. What I'd like everyone to do is it's a 2-step process. I'd like for you to download the workshop files, and then you're going to connect to our workshop. And I'm going to walk everyone through this, right? So I'm going to ask Shubo to post in the Zoom chat, or if you'd like, you can type what you see highlighted in blue here. The first link is what's going to allow you to download the workshop files that we're using just this morning onto your own MATLAB drive. All right, so to begin with, this requires that you use a MathWorks account, we call an MWA. If you don't have an MWA, then when you click on the link that Shubo sends, it will ask you to log in. And if you don't have an account, you can make one instantaneously. And then you'll be able to download the files to your MATLAB drive. MATLAB drive, as you can assume from the name, is similar to like OneDrive or Box, et cetera, right? So it's a cloud-based data storage system that MATLAB hosts for you, right? All right, so let's, my class. Okay, so I'm going to walk everyone through what I'm asking them to do. Hopefully everyone has been able to get access to the link or has typed it in as you see it here. And what I'm going to ask you to do is to I'm going to ask everyone to go to add to my file. On the top left, and then click on copy folder. Okay. So the files that are in my MATLAB drive, we don't want you to modify. We want everyone to have their own local copy. So we're going to copy that folder. Okay. All right. So I'm going to walk around, and I just want to make sure that no one's having any issues with this first step here. So, gentlemen, you're good, or you're still working? Good, good. Okay, gentlemen, good, good. You've copied it. Okay, yeah, good, gentlemen. Oh yeah, no, sure. Let's see. So, you're saying, yeah, okay, yep. So just click on that tiny URL, sir. You're still working on it. Okay, 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 sir, you're good. Yeah, you're good. Good, good, sir, you're good. Yep, good, sir, you're good. Okay, great. Okay, so this is the first step. Everyone will have access to these files for the duration, right? So, but it's important that everyone can download these files because we're going to be using them for the morning workshop. Shubo, any questions online? Okay, anything that I need to address or, yep, good, okay. All right, great. Is Thomas also online? Fine. Okay, should I wait a moment? Because I want to make sure that everyone's able to copy the file. So, yeah, sure. Raise a hand if anyone needs some additional time here. Or so has everyone's clicked on copy folder? Or, okay, yep. All right, great. So why don't we take the next step? And the next step will now be to join the classroom. Now we have a very special or dedicated virtual classroom, so it's important that we go to this particular classroom. Shubo, have you had a chance to put? Okay, great, excellent. Okay, so the next step now is to click on the link into the classroom. And when you do, I'm going to ask you to select Access MATLAB Online, right? So you're going to pick that, push that button there. Okay, so I'm going to click on Access MATLAB Online. And then I'm going to ask you to click on Open MATLAB Online. This will take a minute to start up, but you'll know that you're in the correct location if you see workshop-matlab.mathworks.com. It's important that you see that heading, right? So we're all going to have the same interface. So and you can't just type those letters because there's some authentication that we do on the back end. But does everyone have this URL listed in their browser? Yeah. Not yet? Okay, no worries. Is it still spinning up, sir? Yeah, okay, all right. Good. You know what? Just because. It's okay. Yeah, no. All right. How are other folks doing? Any issues that people are running into? No? Okay, so to this point, then, you should have been able to download the workshop files from my MATLAB drive to your now new MATLAB drive. And the second thing you should have been able to do is connect to the MATLAB workshop using the link that was posted in the Zoom chat. And hopefully by now you have a MATLAB desktop that looks identical or fairly, my MATLAB drive looks a little different than yours, but you have that. So, yeah. And I believe it's called Parallel Computing Workshop 2.0. Is that, yeah? Okay, good. Excellent. Nice. Let's continue. So what we need to first learn is how do we start a pool of processes. Now, at the beginning, some folks mentioned that they've already had some experience with this, but hopefully we can fill in some gaps along the way as we do this. So there are, in order to start a parallel pool, there are 3 ways that we can do that, and I'm going to show you 2 of them here. So let's start with looking at the documentation for parpool, because parpool is the command that we're going to use. Now, what we're going to do today is we're going to use Live Editor to run today's workshop. So raise of hands, who has used MATLAB's Live Editor before? We have a couple of folks, yep, okay. Humasoft certainly has in the back. Yeah, okay, good, excellent. All right, so I'm going to give a very brief tutorial on Live Editor. Live Editor is our notebook-like interface. It allows you to do a multitude of things, but in essence, it allows you to create a story using documentation or text, code, and output. And we can bundle all of that together in this Live Editor. It also allows you to hide some of your MATLAB code by creating tasks and controls. There's a lot of features in Live Editor that I'm not going to describe because it's not necessary. But I'm going to show you the basics of how to use it now. Okay, so, and you don't need to necessarily follow along with, well, please pay attention to what I'm doing, but you don't have to do what I'm about to do. But when I click on a new live script, the first issue that sometimes people run into is, how do I write code and how do I evaluate it and so forth? So when I bring up a, let me close this. When I bring up the live script editor, then you'll see a gray box. And the gray box is where I can enter code. So what I might say is x equals rand, and we'll give it some value. But then when I hit enter, you'll notice that it actually doesn't evaluate it, right? So it's more like a typewriter where I'm just entering the code, or like an editor. And so now maybe I want to plot my results. At this point, now what I want to do is run my code. And so there are several ways that you can evaluate code in a live script. I'll show you one at a time. One way that I can do that is, Okay. So one way that I can do that is by just simply hitting the green arrow, which is the run button. And what we're doing here is we're running or evaluating this cell, not like a cell array in MATLAB, but just a cell. And you'll notice that when it ran the code, that the output is displayed by default on the right-hand side. That's customizable. That's the default behavior. Where I like to place it is actually underneath the code that I'm running. And so on the right alley, you'll see that the output can be displayed on the right, embedded, or it can be hidden. So what I'm going to do is I'm going to select the middle one. This is just my preference. And now you'll notice that when I run the code, it gets displayed underneath. The other alternative is that I can hide the code. And this is when you want to publish your paper. So you might have some text, and then you just simply show the output. But what's hidden is the MATLAB code that you use to actually run the code. We're not going to use that at all today. And as I mentioned, there are a lot of other components of Live Editor, like tasks and controls, almost so there's a low code model. But that's for a different day. All right, so I ran some code. What I want to do is make some modifications to the code and rerun it. So I'll change it from 100 by 100 to be 1,000 by 1,000. And then again, I will just click run, and it will refresh my plot, right? So once the code has finished running, I may want to clear my results. And so if I right click, I can clear the output, or I can clear all. Clearing the output simply clears whatever has been displayed to the command window or to the live script within that cell, and clear output clears all of my results. So in this case here, I'm just going to right click and clear output. And honestly, that's all that's really necessary at this moment. We just need to understand how to add some text, how to evaluate the text, and how to be able to clear the results once I've run that cell, okay? We're going to use this model for our workshop this morning. Okay, so let's get on to our first example. The first example is called parpool_intro, and you can find all the files that we're going to use today in the Parallel Workshop -2.0 folder. So I'd like everyone in the files component, the files widget, I'd like for you to open Parallel Computing -2.0, and you should see a list of some of the workshop files that we will use today. And I'd like you then to click on the parallel pool_intro file, and just simply double click it, and it will bring it up in the live script editor. So parpool_intro. And because we're going to be doing everything within the live script, I'm actually going to just expand the live editor, so it's really the only thing that's being shown. All right, let me take just a moment here and just make sure everyone's gotten to this point here. All right, was everyone able to bring up the first introductory example? Yeah, good, excellent, nice. All right, so I mentioned that in order to run any parallel code, we first need to have a pool of processes that we call workers. And so in order to start up this pool of processes, there's several ways that we can do it. And all of it stems from using the parpool command. So let's take a look at the documentation for parpool. So in order to run the first cell, I'm going to click anywhere in that first cell, and a cell is delineated by the blue line that you see across. So I mentioned that there are several ways to run code in the live editor script. The first is using the green button. In this case, what I'm going to do now is I'm going to come over to the live editor tab, and I'm going to click on Run and Advance. So that's the second way that we can run code. So I'm going to click on Run and Advance. What Run and Advance does is it runs that cell and then advances to the next, but it doesn't run it. And the code that we were supposed to run is parpool, right? So here we are. Here's the documentation for parpool. Parpool, you can just run without any input arguments, or there are several input arguments that you can pass. So without specifying any input arguments, the default for parpool is to start up a certain number of workers. So the question I have for you is, if I want to run some parallel code, and I just tell MATLAB, hey, start up a parallel pool, and we know that a parallel pool is going to start up a collection of workers, how many workers is MATLAB going to start up for me? I know you know the answer, so I'm going to pass on you for the moment. Any thoughts? Any ideas of how many workers MATLAB would start up? Well, let's say I've got 4 cores, 4 physical cores on my machine, and I've also have hyperthreading, which in essence splits the core in half. So I've got another 4 virtual cores. Some possibilities are if a default size of the parallel pool would be 1. So if you don't tell me how many I should start up, MATLAB's just going to start up 1 worker. That's one option. Another is I've got 4 cores. I'm going to start up 4 workers. Or if I have hyperthreading turned on, I'll start up 8 workers. I'll sort of maximize the number of workers I could start on the machine. Any thoughts? Any ideas? All right, so what MATLAB will do is it will look at the number of physical cores you have on your machine, and most people know what that answer is. But if you don't, I'm going to show you how MATLAB deduces it. And there's a function in MATLAB called max num comp threads. So, oh, actually, I'm running this on a different one. Max num comp threads. Okay, so what I'd like everyone to do is type this command. It's what we refer to as camel cased. Camel case means that when you're running or writing the name of the function, that the first word is in all lowercase letters, and then each subsequent word is leads with a capital letter. So it looks like a camel. Okay, so I'm going to assume that when folks run max num comp threads, that everyone comes back with the number 4. Is that correct? Yep. Okay, great. Excellent. So if we're going to start a pool of workers up, then the default is going to be the number of cores on your machine, right? So what I'd like everyone to do is just simply call parpool, okay? So parpool. And so what's happening right now is MATLAB's going off and starting a pool of these processes. And because we didn't give it any input arguments, it's going to start a default size of 4. And again, 4, because that's the number of cores on this machine. And you might even be asking, well, Raymond, where is this machine? This is MATLAB. It's a specialized version of MATLAB Online. And in fact, I should just put a plug for MATLAB Online. Everyone in academia has access to MATLAB Online. It's a fantastic resource. If you want to run MATLAB in the cloud, this is probably the easiest and quickest way to be able to do that. And you can use that with your MathWorks account. So anyone can do what we're doing today. What's different about this is that it's geared for parallelization. So we have additional cores. I think MATLAB Online, you only have either 1 or 2 cores. And this also has a GPU, which MATLAB Online does not. But you have all the same toolboxes that you'll have here today. So, okay, so MATLAB has now gone off and spun up a pool of these workers. You can now see why I use the term headless, because when we start up the pool of these workers, we didn't see additional desktops that are all running. But in fact, these workers are now sitting there idle, waiting for instructions or commands to be sent to it. Okay. And in fact, though that pool of those workers are going to continue to sit there idle for a period of up to 30 minutes. After 30 minutes, if you don't tell it to do anything, those workers will automatically shut down. Has no bearing on the MATLAB client. The client will continue to run, but those workers, if you're not doing anything, right? So let's say you start up a pool of workers, you run some code, and then you go for some coffee, you go, chat with some colleagues. If nothing is happening, those workers just shut down because those are consuming resources on the machine that MATLAB is running. And if you don't need it, there's no point in running it. It's very simple, as you can just see, to start up those workers when we need them. So the first way that you can start a pool is explicitly call parpool. The second is that if MATLAB thinks that it needs a pool of workers, because you're calling a parallel construct like par4, then MATLAB looks to see if a pool of workers are running, and if not, it will automatically start one up using the default. So if MATLAB will automatically start a pool for you, you don't need to call parpool. Why would I need the parpool command? What would be a reason that I wouldn't just let MATLAB start the pool up automatically for me? Nice, excellent. Screwdriver? Yeah, okay. I think that's a screwdriver. Yeah, there you are. Thank you. All right, so exactly. And we're going to see this when we're on Carolina. Carolina's got 128 cores. If we just run a local pool, it's going to be, by default, start up 128 workers. And if I were only running or processing 50 images, it would be unnecessary to start up a pool of 128 workers when I only need 50 workers to process 50 images, right? So I think actually it's a good idea to have more control over the resources that you're requesting rather than just taking the default behavior. Now, there is something that you should be aware of, and that is that you can only have one parallel pool running at a time. So what I'd like you to do is just simply hit the up arrow key, or you can retype parpool if you want, and run it a second time. And everyone should have seen an error getting displayed saying that you can only have one parallel pool running at a time. So why do I bring this up? Well, because sometimes what I'll see in people's code is that they will make a call to parpool and embed it within their MATLAB code. It says, okay, my MATLAB code needs 40 workers, so I'm going to call parpool of 40 and then run my parallel code and so forth. Problem is that when you go to run the code and it runs successfully the first time, but then you make some changes to your code and you rerun your code, the pool doesn't shut down. These are separate things, right? The resources that you have or you need, the cores, and the code that you're running are separate. So therefore, if you run your code and your code finishes, those workers are still running. Now you go to run the code again because you've made some modifications, and the first thing it says up at the top of the code is parpool, and MATLAB throws an error because you can only have one parallel pool running at a time. So for that reason, I typically recommend that if you're going to explicitly start a parallel pool, is that you do it outside of the MATLAB code. Spin up the pool of workers that you need of a specific size, and then run your code. Alternatively, you don't need to call parpool. If a pool hasn't started and your code needs it, it will start one for you. But again, just remember, it will use some default sizes, which may be more or less than you need. So, okay. All right. I mentioned that there's 3 ways to start a parallel pool. I've listed 2 of them. One is to explicitly call parpool. The second is to call that par4 or any parallel construct will start one for it if you need it. And the third is that if you look at the lower left-hand corner, you'll see a blue button. And that blue button allows you to start a pool of processes. So if I right-click down on the arrow, you'll see that it says that I can shut down the pool, or I can look at the parallel pool preferences. So in this case, the reason it says shut down, of course, because one's already running, and MATLAB knows you can only have one running at a time. And that leads us into, well, if we can start a parallel pool several ways, what are different ways that we can shut the pool down? And this is the first way. Well, it's one way, right? So one way is that we can just click the lower left-hand button and we can shut down the parallel pool. A second way, well, okay, let's see what folks know, because there are some people who've done this before. What's a second way that we can shut down a parallel pool? We can use the lower left-hand corner. Anyone know another way that we can shut down or delete a pool? Yes, and how would you do that? Okay, delete. So we can delete the pool. So when we create a pool, we can get a handle to our pool, and then we can delete the pool. So good, excellent. So we can delete the pool. And then the third way is that I mentioned earlier, MATLAB, if the workers time out, will automatically shut those workers down, right? So I said there are 3 ways to start a parallel pool. We're going to show you a fourth one in a moment. There's actually 4 ways to start a parallel pool, and there's 3 ways to shut the pool down. This is the basic operations. Before we run any parallel code, you have to have a pool running. So it's important that you understand how you're going to start the parallel pool and what the default options are, and how you can customize it. So, all right. So one way is that you can, to shut down the pool, is that down the lower left-hand corner, we can click shut down pool. Another way is that you can type P equals GCP. GCP stands for get current pool. And this is actually, turns out to be the 4th way you can start a pool. GCP will return a handle to your pool object, but if one hasn't started, it will start one for you automatically. So this will return a handle to our pool object. And now that we have our variable P, if we wanted to delete the pool, we could type delete P, and that will shut down our pool, okay? Notice that MATLAB was keeping time, right? It says, well, it's been up and running for about 9 minutes, and had it gone another 21 minutes, you would have seen that MATLAB would have timed those workers out, so. Okay. We're going to start talking about the parallel language more, but before I do, any questions on parpool and how it operates? Yes. Yep. So mine started with 8, or yours started with 8? Yours started. So let me just make sure. Yes, it's these fingers that has this, no.
Num workers, that's what he's referring to, I think. When you look at the parpool, then you have number of workers, and that's 8.
Okay, yeah, let's see. But yours started with 4, is that right? And mine started with 8. Okay. That's right. It does. Yes. Yep. Exactly. Let me just check. Interesting. Okay. Let me check 2 things. Is that, and then. So at some point, what I must have done, and I'm not sure because this is not really my cluster. It's not my, I'm using the same online session that you are. But we're going to talk about profiles in the afternoon. There are local profiles that we're using this morning, and for mine, I've set 8. So yes, I don't know why. Did anyone else start with 8? I find this a little odd. Shubo, can yours start with 8? Oh, there's a question. Oh, no. That's not. Shubo, do me a favor. Can you just take a picture of that? Thanks. So good catch. Excellent. What do you like? Glasses? We're good. Deck of cards. There you go. These are great, actually. I mean, they're all the same number, the same card, but anyway, so, all right, good catch.
Raymond, there's a question online. I can answer it, but just in case anyone else has it, do the workers remember states from previous runs of a MATLAB script when rerunning?
Okay, so the question is, are the workers have state or are they stateless? When the workers shut down, it's just like shutting a MATLAB client down. It does not retain state. So, good. Okay, good, nice. So now that we understand how we're going to launch a pool of processes that we call workers, the question now is, what can we do with that, right? How do we layer on top of that our MATLAB parallel language? And so the first thing to be aware of actually is that MATLAB has extensions called toolboxes and block sets. And those toolbox and block sets have parallel enabled functions added to them. What do I mean by that? Take the optimization toolbox. The optimization toolbox has, if anyone's used optimization and has looked at the optim set function, it has a way of using parallel in the algorithms that we're running. And you can opt in to parallelization when you're running your code. Now that might seem a little odd, right? Here we are, we have MATLAB, we have the parallel computing toolbox. Wouldn't we want everyone using the parallel computing toolbox? Why would we want users to opt into parallelization rather than just by default always enabling it? And that's because you understand your code, we don't, right? We don't know how long it takes to run your code. We don't know how large your data sets are. So you really have to understand how long it takes to run your code and whether it makes sense to use parallelization for your code. But as you're going to see, sometimes it can be actually quite simple to be able to do this. Again, every toolbox or block set is different. And first of all, I mean, not all toolboxes and block sets have parallelization built into it. So you need to take a look at your documentation and to see if there is any capabilities. But this regression learning or classification learner, by just simply selecting the button Use Parallel, we'll start up a pool for you if it hasn't already started, and then we'll make use of it. Or, as I was mentioning earlier, the optimization toolbox, right in the code, you can just specify to use Parallel and look at how fmincon and others are using it. But that's a very small subset. By and large, people have to write their own parallel code, and you're going to do that using parallel constructs like par4, par-feval, SPMD, and so forth, right? And so that's really what we're going to be focusing on for the rest of the day. Are there any Simulink users? 1, 2? Okay, so I'm going to touch upon how we can speed up Simulink models both in the morning session and in the afternoon. By far, the most common parallel construct is par4. And that's because most people are writing for loops that they want to speed up those iterations. And so it makes the most sense then that, in fact, par4, parallel for loop, would be the most common construct. There are a multitude of ways of speeding up your code. We're not going to talk about all of them. We're just going to highlight a couple of them. But I assure you that there's other ways that we can think about speeding up your code than just using a par4. But there are 2 basic tenets of using a par4. The first is that the tasks that you're running have to be able to run in any order. And the second is that the tasks are order independent. I'm sorry, the tasks are independent of each other. Okay, this is sometimes what we refer to as embarrassingly parallel. In fact, anyone who's familiar with parallel processing or parallel programming understands this notion of, creating out an MPI ring and having the processes or the ranks talking to each other. That's not what's happening with a par 4. It's embarrassingly parallel because we're just having all of these workers starting up on their own, and then we dole out tasks to them. They just run it in parallel. They return the results back to the MATLAB client, and that's it. We do have MPI layer. We have a layer to MPI programming that I can talk about when we talk about SPMD later. Okay, so you might think, well, run in any order. Okay, fine. That's pretty straightforward. Well, think about some of the code that you write that says, well, wait a minute. Actually, the code does have a certain dependency in the order that I'm running in. For instance, if I have for loop for I equals 1 to 1,000,000, and then I say, well, if I've met some threshold, I want to exit early. Okay, that's not parallelization, right? So the order, or when some event happens, then we might actually terminate early. I'm going to show you a different way that we can address this. So par 4 has very specific tenets. You have to run all the iterations. We cannot abort early. It has to be able to run in any order, and they cannot depend on each other. There's no communication from one process to another. So if I'm doing some edge detection on one image and I'm doing it on another, as long as I'm not trying to do any cross correlation between one and the other, that's fine. But once I depend on if I'm learning from one image and applying it to another image, that's not parallelization, or the way that we're doing it with a par 4. So, right? Very fundamental, very simplistic. Okay, so how are we going to do this? We're going to be able to, or ideally what we'd like to do is take a collection of tasks that are running in serially, and we want to be able to run them in parallel. And so what we're trying to do is reduce the amount of time. Now, start thinking about some of the complexities about that, right? You're used to, at this point, having one process, the MATLAB client, doing all of the work. So if you were writing to a file, you know that there's only one process writing to that file, so you'll have no file contention. But what happens if you have multiple processes that are all doing the same thing at the same time, not only just reading from a file, but writing to a file? How would you address that? How would you think about, oh, well, wait a minute, I've got 10 or 100 processes all trying to write to the same file? So those are some complexities that you have to think about. And we'll talk about how to deal with load and save in a couple examples this morning. Here's a pretty simple example. We're going to assign A, or we're going to pre-allocate A to be zeros of 5, 1. So this is a column vector. We're going to assign B equal to the const of pi, and then we're going to have a for I equals 1 to 5, and then A of I equals I, which would be 1, 2, 3, 4, 5, plus our pi constant, right? You look at this and you say, I can run this in any order, and I will always get the same results. And that's the key. It has to be deterministic. And one good test is that if you can run your for loop in reverse order and get the same results, then that could be a good candidate of something that you could run in parallel. Okay? All right. So the way that we're going to do this is we're going to take our for loop and we're going to rewrite it as a par 4. And I'm using that term very specifically. It is a rewrite of a for loop to a par 4. We're not just simply adding 3 blue letters. The reason I say rewrite is in a couple of examples, you'll see how we have to actually change our MATLAB code so that it can go from serial to parallel. So, all right, on to our next example. So what I'd like everyone to do is bring up par 4 underscore getting underscore started. Okay. So in this exercise, you're going to learn about how to write a parallel for loop. So let's take a look at the documentation for par 4. And we now know that if we want to evaluate a cell, we can just simply select the cell and run it using the triangle to run all of it. Well, we don't want to run all of this right now. We can click on Run in Advance. But what I'm going to show you is a third way to run code, and that's just by double-clicking the blue bar. Now, this, by double-clicking the blue bar, it evaluates the cell. It's not going to advance to the next cell, but I want to incrementally show you different ways that you can use Live Editor. So this is the next way. It's pretty simple, right? So the par 4 looks very similar to a for loop, but the other constraint for a par 4 is that the indexes or the loop variable. So in this case, if I say for I equals 1 to 1,000,000, I is the loop variable. The loop variable has to be monotonically increasing, and it cannot have any step size. The step size has to be 1, which we know wouldn't make any sense to add in there. So it's going to be from 1 to 1,000,000, not in step sizes of 2, 4, 8, and certainly not in step sizes of 1, in step size of 0.5 and so forth, right? So it has to be monotonically increasing. But other than that, it operates just like a for loop. I mentioned to you that there are different parallel constructs. You'll notice that you can put parentheses around the loop variable and M, right? So this is not something that you would see in a for loop, but there are other ways that we can call a par 4 that we're not going to discuss this morning, but there are other ways that we can do this. All right, so we're going to learn about the par 4. So let's drop back over to our lab, and we're going to click on the next cell. So the next cell is from 2 to 7. What I'm going to do is I'm going to ask everyone to go through this on their own, but let me just give you a highlight of what you're being asked to do. Run the first block of code. A gentleman in the back mentioned that using TikTok is one way of timing, and that's what we're going to use here. So I want you to tell me how long it's going to take to run this code. And then I would look for the to do, and I would like for you to rewrite this block of code using a parallel for loop, and then rewrite it again for exercise 3. Okay, so we'll take 5 minutes. Okay, I've got 17 after. We'll take 5 minutes, go through this exercise, and then when we come back, we'll go through the solution, and then we'll take our first morning break. Thank you. Okay, so to no surprise, when we run our for loop serially, we have 1, then 2, then 3, and it takes 10 seconds to run. So this would be something that perhaps we could parallelize as well. Notice that, what makes this a good candidate is that we have a consistent amount of time that it's taking is pause of 1, right? So we're not going to be able to speed up pause of 1 any faster, right? Pause of 1 will always take 1 second, right? But we're running this 10 times. And so perhaps we could parallelize this. But also MATLAB doesn't assume that your code is going to take the same amount of time. So perhaps maybe a slightly more interesting example and realistic is if we said pause of, maybe 5 times rand, right? So now let's go ahead and you don't have to run this, but let me just okay. So now it's running sequentially, but it takes a different amount of time each time and so forth. This is probably more realistic, and it actually gets into how MATLAB schedules its jobs. And there was a question about that. And when we rewrite this as a par 4, I'll address how MATLAB handles this, right? All right, so there we are. It's finished all. Now, obviously, it's not going to take 10 seconds because we now have 5 times rand. So this will be different each time. All right, so let's go ahead and rewrite this. So now I'm on the second section, and line 10 says that we need to rewrite this as a par 4. So there I go. And I'm going to keep pause of 1 just so we have some consistency. And I'm going to run this section. So what I did, and this may not be the case for everyone because maybe you already had a pool that was running, but if I start up MATLAB for the first time and I run this code, notice that MATLAB sees that it needs a parallel pool to run. And so the par 4 is there and says, well, okay, I'm going to go off. And actually this might be, unless I change it, maybe this is still going to be a pool of 8. But now it's taking time to start up that parallel pool, and then it will actually run my code. So I don't need to call par pool. If MATLAB sees the par 4 and one hasn't started, then it will automatically run the code, start the pool forming. So, okay. All right. Now, the first thing that you should have noticed is that when you did this, in fact, the iterations are happening or are being displayed in different orders, and your order is going to be perhaps a little different than mine. And this goes to the fact that MATLAB is going to run the iterations perhaps in any order. We do have sort of a schema for how we try to figure it out, but let me talk about load balancing. And so there was a question about, do we have any control over if I've got 8 workers and I've got 80 tasks, can I give each worker 10 tasks, or which 10 tasks can I give it, and so forth? Because MATLAB doesn't assume that each task takes the same amount of time, what we do is we build load balancing into it. And what that means is that, let me equate it, I apologize, to the US, where I'm a little more familiar. We have 50 states, and you could imagine that if I wanted to do some census data on each of the states, that I might have 10 machines, or 10 workers, and I'm going to assign each worker, 5 or 10, states or whatever, right? But if I were to throw the work at the workers, and I said, okay, I'm going to give everyone 5 states. There are some states in the US, I'm sure just like in Europe, where it's more densely populated than others, right? So if you've been to the States, states like California, Texas, and Florida are more densely populated than, for instance, where I am up in Boston or, the northern areas. So some workers would actually be done with the work quicker than other workers were because it's more densely populated for my algorithm. So what MATLAB decided is what we're going to do is we're going to give each worker just like 2 or 3 tasks. And then we're going to give, as the workers finish the work, we're going to give it more tasks. Some of the workers will still be finishing work while more work is being sent to the workers. And the idea is that all of the workers are busy at the same amount of time. And then there'll be sort of this tail end, where at the tail end, maybe there's a couple of workers who are just finishing up some work at the last minute. Now, this is what we mean by load balancing. We give a certain amount of work. As work is done, we actually give it more work and then less work towards the tail end. There is, in fact, a way that you could design your own schema. It's a more advanced way of doing it. But I mentioned in par 4, there's that M argument, if you look at the documentation. And in there, you can specify that you want each worker, worker A, to have 5 tasks and worker B to have 15 tasks, if that's what you choose to do. There are other reasons why you would use this model, but we won't discuss that for this morning. So, but yeah, so you could customize it, but our recommendation, you just let MATLAB figure out how much work to give each worker, and it tends to work quite well. All right, so what we saw was that when we ran the code the first time, it took, I think it's like 45 seconds to run. That's because the timing included the overhead of starting up the pool. If we now take the last example, and rewrite this as a par 4, and then run this section, we'll see that it gets displayed in any order, and it takes 2 seconds to run, okay? Because the pool has already been started, we're not accounting for that. So here's my question. If this if this takes 2 seconds for 10 iterations, I'm going to throw 15 iterations at it, and I'm going to run this section again. Yes.
Can I have a short question? How it is possible that it took 2 seconds for 4 workers per 10 iterations?
Yeah. Because I'll have to look when I set this. I have a pool of 8 workers that are running. That's why. But here's my question to you. Okay, that's your question to me. Now here's my question to you. I ran 10 iterations in 2 seconds, and now I ran 15 iterations. Also takes 2 seconds. How is that possible?
It waited for the last job to finish.
It waited for the last job to finish. No. I mean, I could throw, you know what? I'm not even going to throw another iteration at it. Okay. So I'm going to throw, let's see how far I can go with this, right? So I'm going to throw 16 and I'm going to run the section. There's 16, still takes 2 seconds. All right. I'm going to give away the answer without telling it to you. I'm going to go 17. How long is it going to take to run this? 3 seconds, right? And that's because we get right. So there's this modula, right? That if I've got a certain number of tasks that I want to run, the size of the pool should be proportional to that, right? If I've got 100 images to process, it doesn't make sense to start up 70 workers, even if I have access to 70, because 20 of them will be sitting around doing nothing while the other 30 are doing some work, or I probably have it backwards, but right. So if I have 100 images, I would start up 20, I'd start up 50, maybe 2, but things that where, because what would be the point? But this also, of course, goes under the assumption that it takes the same amount of time for each one, right? If it's a random amount of time, then perhaps, yeah, sure, throw more workers at it and so forth. So, okay. All right. The last part of this exercise is that you need to close down your pool. So I'd like everyone to take a moment and close your pool down. You know several ways to do it. Pick one way, and then we are going to 2 minutes over. Well, I shouldn't have asked that last question. So we're going to break for 15 minutes, and then we're going to come back and we're going to talk about ways that we can even improve par 4. So any questions? Nope. Good. All right. Thank you, folks. We'll be back in 15. Okay. All right, folks. Why don't we get started? Yep. Good. Any questions of what we've gone over so far this morning? We've learned about a par pool, right? That's the basic foundation of running a collection of workers, and workers are headless MATLAB processes. When we started a pool, we can control how many workers are started, or we can use the default. And we noticed that when the workers did start, that we didn't see all these new additional desktop environments, but instead they're sort of just running in the background. And then par 4 can now make use of those. And we learned that a par 4 will start up a parallel pool if one hasn't already started. And that we have load balancing that says that we're going to try to have some intelligence about how much work each worker is getting so that they're all busy at the same time. And there's certain customizations with par 4. We didn't really go into a lot of them, but we can customize the schema or how tasks are broken up across each worker as an additional argument to par 4. So, but some of the tenets that we learned about it is that it has to be order independent, task independent, and that there's no inter-process communication that's happening between them. We learned that the variables, the loop variable has to be monotonically increasing, and so forth. And there's just no step size, right? We can't terminate early, so there can't be any conditional statements that says if we've met some condition, then we want to stop early. So there's certainly some rigidness to par 4, right? Imagine that your code takes 10 weeks to run and you can get it down to 1 day. One of the drawbacks is that as it's designed right now, we don't have any way to get any intermediate updates. You know, one of the questions I'll get is, well, how do I know it's doing anything? Because honestly, this does take days, if not weeks to run. The code is running, but I don't really know how far along I'm in with my code. So what we've done is we've added a new feature to par 4 called a data queue. And the data queue is the ability for the workers to send data back to the client on its own. Well, what do I mean by that? When I run a parallel for loop, MATLAB is going to take the body of that code and send the code and the instructions and the data and send it to each one of the workers. So it's in one direction. Almost sounds like an American band, One Direction. I think that's what my kids listen to. But anyway, so in going in one way, the client sends information to each one of the workers, and it does have the ability to bring the results back to the MATLAB client, but it's all being managed by the client. What a data queue allows is the ability for you to create a channel from the worker to the client. And so we can send some data through the data queue, and then the client will be listening to that data queue and then can operate on the data queue. So why is that important? Well, because now what we can do is while the parallel for loop is running, the MATLAB client can do other things while it's running, including updating images. It could be updating plots. It could be writing files to a database or a disk locally on the client's machine. So let me, yeah, I thought I was, okay. Right inside the example. All right, so a data queue is going to be first created on the client side, right? So what you'll see here is that we're interweaving serial code with parallel code, okay? And the first thing that we're going to do is we're going to create a data queue. The data queue is going to be assigned to, in this case, the variable D. It certainly doesn't matter what the name is. And what we want to do in this case is we're going to run a for loop, and then we're going to send back some information through the data queue, and then MATLAB is going to update a wait bar that tells us how far along we are with our for loop. Now, the thing I should mention is that this is simply an example. When I show this example, inevitably someone will ask, well, because we'll do an exercise on this in a moment. Where's my wait bar? This exercise or the concept of a data queue is not about a wait bar. We're simply using a MATLAB wait bar to graphically show how far along we are with the code. You could write a print statement. Again, you could write files to disk. It doesn't really matter what you're doing with that information. But in this case, we're trying to kill two birds with one stone. We're pulling some data back from the MATLAB workers to the client. And what we're doing with it is just updating a wait bar, okay? All right, so how do we build this? We have our data queue. Separately, we're going to create a wait bar, which is displayed down here. And then after each iteration is completed, or as we get information from our data queue, we're going to call a function, n update wait bar. Now, who can tell me what that @ sign is representing? What in MATLAB, what do I use an @ sign for? So what we're doing is we're going to run this code after an event has happened. That event is that data is being sent from the worker to the client. The reason that we have the @ sign is because we're assigning a pointer to the function that we want to call, right? So we're delaying when this function is actually going to get called. We don't want to call update wait bar right now. We're passing in a pointer or a function handle that says that when an event has been triggered or fired, we want to call this function. So we're going to call this at a later time. And to delay that, we're going to pass in a pointer to that function. We're going to assign n equals 200. So we're going to run 200 iterations. And then P is going to be a local counter that is what we use to update, whether we're 100th, 200ths, and so forth, or 20ths along the way. Then we have our for loop for I equals 1 to 200. We're going to calculate A of I. And then in this case, we're not sending A back, but we're just sending back the loop variable. Now, we've learned that the loop variable can run in any order. So in fact, the I in this case could be 3, then 7, then 100, then 217. It doesn't really matter because in fact, in this example, we don't actually make use of the variable I. When we update our wait bar, we have this local counter P, and that's what's allowing us to know that we're 1 200th, 2 200ths, and so forth. Now, before we go through this example or run our exercise, I have a question about this function right here, because notice that this function is referencing the variable P that was assigned right here. So how is that happening? This is not a local function. What kind of function is this? Nested function. Very good. Excellent. You don't have to use the nomenclature n, but that is certainly a hint that this is a nested function. And a nested function is a function that's nested within an outer function. And the benefits of a nested function is that it provides scope to the variables that were referenced outside in the outer function. And because you have access to it, you have you can read those variables, and you can also modify those variables and so forth. So this example right here, the main focus is on creating the data queue and then doing something after something happens. That's it. It's not a focus really necessarily on weight bars or on nested functions. Those are just things that we're using to show this example, okay? All right, so we create our data queue, we create a handle to our weight bar, we assign the name of the function to call after each event has happened, and then I don't want to use the word nested, embedded within the par4 is that we want to send something, in this case, the loop variable I, back to the client, and the client can do anything it wants with it. And then once a worker has finished and has sent the client back something, then we're going to do something, whatever. In this case, we're just updating a weight bar. So, okay. So the data queue allows us to get intermediate updates to running our parallel for loop. This par4 still has to run to completion, but now we can see, how far along we've gotten and so forth. So this is one example of how you use a data queue, but again, it has nothing to do specifically with weight bar. All right, so let's jump into our next exercise, and that's going to be data queue _ getting _ started. All right, so what are we doing in this exercise? Imagine that we are proctoring a quiz, and we're going to dole out a quiz to several hundred students, and we're going to we want to monitor how long it takes the students to take the test, and we want to see what the grades are that they're getting, right? And in fact, maybe what we want to do down the road is even terminate the test if too many people are failing. If we just see that the grades are coming in and people are getting very low scores, we're going to cancel the test and so forth. But in this example here, we're going to give everyone the same test. It takes a certain amount of time. They've been given, we'll say 5 minutes. And we want to see what the grades are that they're going to get when they're coming back, okay? I'm going to walk through this example, and then I'm going to give you a little time yourself to actually implement the solution. So in this problem, we're given a quiz to, in this case, 20 students. Each student will finish in a random period of time with a maximum of 5 minutes. And each student will get a random grade between 55 and 100. What we want to do is just plot the distribution of our test. We need to gather all the scores to plot the results. So that's what we're going to do at the end of the test. But we also want to write the results of how long it's taking to run the test as they've happened. So the first thing that you're going to need to do, and so you'll find each of the sections, there's a to-do. So you have to create a data queue object, and you're going to label it Q. And then after each quiz is taken, log the grade. So from the queue, you're going to get the grade. So we're going to need to assign an after each function. And I will tell you that the name of the function that you want to call is post grade. So we're going to post the grade that the students got. And then this is the code that we want to call, right? So we're interweaving, again, serial code right here with, oh, well, I guess I gave it away, but that's only part of it. So you're going to rewrite the for loop to be a par4, and you have to give the quiz. Now, to give the quiz, what we're going to do is we're going to give a range of what we think the answers will be, or the scores, and that range is going to be a low of 55 to a high of 100. And then, and I think that is, yeah. And then, of course, we have to pass in the queue that the code will use to send the data back. We will then, once the quiz is done, then we will chart all of our grades. The helper function that you have to implement is you're going to be passed a range of low to high grades, in this case 55 to 100, and you'll be passed in the queue that the workers are going to send results back to. So here is your last action item, which is you're going to call the send, and you're going to pass back through the queue the grade, and the grade is listed right here on line 36. And I think that's, yeah. And then the last pieces here are just to post the grade, which in this case is just going to print it to the command window, and plotting, which will happen when everything's done. So you have 1, 2, two, three, four actions to do. The first is to create your data queue. The second is after each, you need to assign a function for the data queue to evaluate as an event comes back. You have to give the quiz, which is going to pass in the min and the max, as well as your data queue. And then the last thing you have to do is call the send command using the queue and the grade that the student received. Okay, so I'm going to put back here the example that we use. Now, again, there is no plotting. I mean, there's no weight bar. In fact, what's getting displayed is just the grades as they finish, right? So we're going to have a parallel pool that's running, and then we're going to have to create a data queue. We're going to have to assign what function to run after each event, right? So it's listed almost like that. You're going to have to send the grade back through the data queue, and then you have to, and then the plotting will happen at the end. In the example, I used the variable Q. Here, they're using the variable D. I would say use Q just because that's what I have in the example. But as we know, the name of the variable doesn't really matter. Okay. All right. I'm going to put 5 minutes on the clock. And then I'll walk around if anyone's having any questions to answer. So, but look at this as a sort of a pseudo template, and then look at your to-dos to finish. All right. I was walking around and I saw some bar charts, so that's looking encouraging. Let's go through this example together. The first thing that we need to do is to create a data queue. Now, again, a data queue is created, in this case, on the client side, and it's going to be passed to the workers in the parallel for loop, so that the workers on their own can send data back to the client, and then the client can do whatever it wants with that, right? So we'll create parallel.pool.data queue is our first step, right? So there's our data queue. And then we have to assign it a function to call. So after each iteration or each piece of data comes back to the queue, we want to call a function. In this case, we're going to call our local function local post grade. And we're still going to be using a parallel for loop. So line 19, if it wasn't already, should now be a par for. So for student ID is equal to 1 to the number of students, and we need to give the quiz. And so when we give the quiz, the helper function says that it needs a grade range that it's going to use, and then it needs the queue that it's going to send the data back to. So let's pass in our range, and our range is going to be from the low grade. So we have a low grade of 55 and a high grade, which will be 100. And then we're going to pass in the data queue as well, right? The function is going to return the grade, but what we'll also do is we're going to pass back the grades as they happen. So we'll plot the grades later, but we're going to send back through the data queue our grade. In this case here, rather than taking 5 minutes, we're just going to pause for some amount of 5 seconds or so, and then we're going to have a uniform distribution from 55 to 100, and that will be our grade. So there it is. Those are the 4 things that we have to do. We're going to save the code. And let's go ahead now and run the code. So I'm going to start from my data queue. And the fourth way that we're going to run our live script. So the first one I mentioned was clicking the green button to run everything. The second was to run in advance. The third was to click on the blue bar on the side. And the fourth now is going to be to run to end. So the reason I'm not running everything is because I don't actually want to run the first section, which is bringing up the doc. So I'm going to select the selection that I want to start in. This will be right here in this cell right here. And then I'm going to run to end. Yep. Maybe I wasn't in there, but all right. So there it is. MATLAB is starting up the parallel pool. This was, yeah, earlier. Before the break, I shut down the pool. So that's what this is here. So notice that the grades are starting to come back now, right? They're coming back. It looks a little scattered. That's because I have that pause of 5 times ran. So they're not all, not everyone's taking the same amount of time to run or to take the test, right? So here, as a proctor, I could be monitoring as these are coming back. And then I plot my results at the end, right? So I'm gonna tweak this example in the future so that what comes back is maybe how long it took to take the test. If I notice that some people are finishing very quickly, or again the grades are too low, that I'll terminate early. But in this example, because we're using a par 4, we have to run the entire. We have to proctor the entire quiz. We can't terminate early here. But we're seeing the grades as they're coming in. But also, as once we're completed, then we'll display our bar chart. I also have data tips turned on, so I can see what the grades are in my live script and so forth. So, okay. Who was able to get this working all the way through? Nice, good, excellent. So this is not a feature a lot of folks are aware of. Certainly those who are using par 4 in the past, they're aware of. They've used par 4. Data queue has been around for a couple of years, but we don't see a lot of people using. But it's a really good way of pulling in data from the workers while the workers are still running, so you could do something with that, right? So, all right, good. Now, one of the things I've been mentioning quite a bit is that a par 4 has to run to completion. But what if the code that you were running is more like we're looking for a local minimum, right? And once we've found the minimum, then we want to stop, right? We don't need to continue with our entire parameter sweep. We're happy with maybe if only 80 or 100,000 simulations run. We don't need all million and so forth. We're looking for something, and once we found it, we want to terminate, right? Sometimes this might be referred to as a needle in the haystack problem. But I mentioned again that par 4 runs to completion. And so that would be a waste of resources, a waste of the workers doing something that at some point we no longer care about. So I'm going to introduce a new parallel construct called par feval. I say new today, but it's been around for quite a while. And the idea is that rather than using a par 4, we're going to use 2 for loops. Well, at least 1 for loop. That's the main thing. It still requires a parallel pool. So that doesn't go away. But what we're going to do in this example is, so for I equals 1 to a certain number of iterations, we're going to call par feval. Now, one of the things that you'll notice, par 4 was highlighted in blue. So that's a built-in keyword. Par eval is not built into the MATLAB language like par 4 is. So par 4 is going to take a pointer to the function. So we're not going to call, in this case, what we'll do is for I equals 1 to 10, we just want to create a bunch of magic matrices, right? So magic of 1 will be 1, then magic of 2 will be 2 by 2, and so forth. We're going to pass in the number of output arguments to calling our function. So there's going to be always one output, and then the next input argument is going to be the number of input. It's going to be the input argument list to calling magic, right? So IDX will be 1, so it'll be magic of 1, magic of 2, magic of 3, and so forth. Okay, now the thing to be aware of, this is it's not asynchronous. That is, this for loop will be blocking until it finishes, but what it's finishing is submitting the job to the workers. It doesn't have to wait for the job to actually finish. So these tasks, or we use the variable f sometimes because it's a future. These futures don't have to finish running before MATLAB can continue running. So this actually starts getting into asynchronous programming. That is that we are submitting these tasks to the workers, but we're not waiting for the tasks to finish. This allows us to do other things, running some other code, plotting, whatever the case is. But at some point now, we need the results back. And that's why in this example, we have a second for loop. So although this is required, technically, this is not required. Depends on what you want to do with the results. Maybe you don't have any output. Maybe you just want to launch a bunch of tasks to go out and set up some listeners, and those listeners are doing something, but we don't actually need to do anything with them. But in this case, what we want to do is we want to fetch the results. And what we're fetching is the result of calling magic of 1, magic of 2, and so forth. All right, so here's my question. I mentioned that when we call magic, that there's going to be one output argument, right? But when we have our second for loop set up and we are fetching our future, that I have 2 outputs. So why is that? Why, if my function only returns 1, am I actually returning 2 outputs? Exactly, right? So just like a par 4, great job. Just like a par 4, that for loop can run in any order because we don't really know how long it's going to take to run this, right? So what we need to know is the lookup value says, oh, okay, the future that came back was 0.7, but that maps to the 17th task that we submitted and so forth. And so you could imagine that if we wanted to plot the results, for instance, this would be our X, this would be our Y. It wouldn't matter the order that it came back in as long as we knew how to pair the results. What I'm not showing here, but is something that we can do, is we could look at the value. And if we've met some threshold, then we could then at that point say we want to cancel all of the futures. That includes any futures or tasks that are currently running, as well as those that are in the pipeline. So if I'm running 1 million tasks and I've only got 10 workers, you could imagine that the majority of the tasks still are being queued up to run. If we have found what we're looking for, we can cancel whatever's running, plus anything that's still in the queue. This becomes quite powerful, right? There are reasons to use par 4, and there are reasons to use par eval, and there's not really a lot of overlap. One is where we want to run everything to completion, and we only want a certain number of workers running. Par eval says that we want to be able to terminate early and so forth. So, and also that, with par eval, we can run other tasks or other code rather than waiting for this to finish. So, all right, good. So we're going to assign tasks to each one of the workers. They will complete, and then using the fetch next function, we will fetch the results. So, it's a little different than par 4, right? Par 4, we can use things like a of I equals, and that is the fetching, right? So if I say par 4 I equals 1 to whatever, and then a of I equals my function, that that is the fetching. But with par eval, we have to use this API that says, well, okay, now that we have something stored in our future, now we have to go and take this extra step to fetch it. We don't have the seamlessness of just returning the results and assigning it right into a matrix. So, all right. So there are advantages to using par 4. You can run everything to completion. There's load balancing. There is no load balancing in par eval, because when the task, when you create a task, it automatically is getting assigned to a worker. So every worker is getting assigned a task, and then as soon as that task is done, another one will. Versus par 4, we're going to give a subsection or a subset of the tasks to run and so forth. Is a question?
Yeah, sorry, I just wanted to ask for the previous slide, what happens if we call the fetch before any of the workers finish processing? Does it wait for any of them and then continues?
Yep. Great. Yeah, good question. I skipped over that, didn't I? So unlike the first for loop, which is not blocking other than just to actually run the for loop, in this case here, the fetch next is blocking. So that blocks MATLAB until there's something to actually fetch. It may come back very quickly. We can do something with it, and then you're back in the loop, and you're waiting for the next iteration to finish. So, yep, good observation. So, nice. Yep. So, the advantages of par eval is that we can get intermediate updates. We can terminate early. There's just no load balancing built into it. So, all right, let's jump into our next example, which is our plotting. So par eval underscore plotter. And for this one, we're going to do this together. Now, LiveScript has a lot of advantages to it, but I will say there's one drawback to it that is exposed in this example. The plotting doesn't finish until all the plotting is done, and this exercise is all about how can we calculate and plot results as quickly as possible. So you will see that when we run this example, that there's one little glitch that I'll explain as it happens. All right, so I'd like, let's run this first section right here, right? We're going to, for I equals 1 to 100, and actually, let me check one thing. Okay, perfect. All right, so let's go ahead and run the first section. Right here. So let's just run it to see what MATLAB needs to do. So we're going to just run the section. So for I equals 1 to 100, we're going to pass in our index value. We're going to calculate y, and then we're going to plot the results. Built into the calculation, it's just going to return a random value, but it's going to also pause for 0.1 seconds to run. So this should take about 10 seconds to run. When we're plotting our results, actually, we could do this in any order, right? So this is a good example where we could plot the last value and then the first value, and we'd still get the same results at the end. So this would be a good example of what we could parallelize, right? All right, so let's take incremental steps into taking this code and actually parallelizing it, right? And we're going to use, initially, we're going to use a par 4, right? So it took 10 seconds to run because 100 iterations, and each iteration down at the bottom is pausing for 0.1 seconds, right? Okay, good. So let's go ahead and I'm going to let's clear our all of our outputs. So right click and then clear all outputs. And let's rewrite it as a par 4. And I'm just going to run this section right here. So how many people got a blank screen when they ran it? Yeah. Okay. Okay. Who can explain why? And let's take a look at that par 4 and explain to me why the screen is blank. What I'd like you to sort of, the mental model I'd like for you to have is that everything that's happening in that par 4 is happening on some other machine. Imagine that, right? In fact, this is all running locally, but really it could be running anywhere. So if that's the case, where's the plotting happening? It's happening on those workers, right? And those workers, yes, they're sitting here, but they're headless. They have no display, no desktop. So in fact, the reason that we got this, the axes to begin with is because we created a figure on the client side, but everything that's happening here is happening on the workers, including this plotting. Okay, well, so that makes sense. All we're going to do is we're going to take the plot and we're going to move it outside, right? So take this and let's just move it outside. I'm going to clear, right? So we know how to clear all the output. And yeah, okay. So now we're going to go and what I'm going to do here is I'm just going to clear all. Okay. And I'm going to run the section again. Well, we're not really getting much farther here. And the problem is twofold. The first is it says that unrecognized function or variable IDX. That seems kind of odd to me, right? I mean, IDX is literally right there. Notice the code analyzer has put a squiggly mark under there that says, well, no, actually, you're doing something wrong, Raymond. So my question is why is it unrecognized? Why is IDX not defined at the end of the par 4? And to answer that question, my question will be to you, what do you think the value of IDX is? Well, I'll give you two options. It could be 1, it could be 100. There's really 100 options, right? MATLAB runs the parallel for loop in any order. So therefore, IDX, the first time around could be the last time it runs. It could be 47. And when you run this code tomorrow, it could be 98. I said earlier that when you run your parallel for loop, it has to be deterministic. You have to get the same results every single time. So what MATLAB does specifically with a par 4 is it makes IDX, it's a loop variable, but it's almost like a temporary variable that's created on the workers. I mean, it's created on the client side, but there's no value after the parallel for loop. That's very different than a for loop. But in a for loop, it runs serially. You know, every time you run that for loop, at the conclusion, the loop variable is the last value of your loop, right? So here, IDX is not being defined when you use it as a loop variable. Okay, so what are we going to do? I'm going to change and this to be 1 to 100, and I think that's going to do it. Well, that didn't really help, right? First of all, we don't have a variable y, and the reason that we don't have y is because in this case, y is now referred to as a temporary variable. Because here's the next question: what is the value of y? Right? Again, just like IDX, y is being overwritten by every single worker. Every worker thinks, well, my value of y is this, my value of y is this, right? So in this case, on line 7, y is referred to as a temporary variable. And what it means is that the workers don't actually bring the data back to the client unless it is one of 2 types of variables: a sliced variable or a reduction variable. I'm not going to talk about reduction right now, but I will explain about slice. Slice means that we're going to slice the variable using the loop variable IDX. And I'm going to run this and then explain. So now what we've done is we've created a vector of Ys, and all of those Ys now are being brought back to the MATLAB client, and now the MATLAB client can work with them, right? Because it says, well, I have IDX 10 and 17 and 30 and so forth, and I have mapped all those values for the appropriate Y, right? The last problem, though, is that none of the plotting happened until after I was done with the calculation. So I've sort of lost some of my value. Previously, when I was running my for loop, I was seeing the updates happening instantaneously. It was just taking a long time because I had to go through every single iteration. What I want is the best of both worlds. I want to be able to get the calculations to happen instantaneously. And as it happens, I want the plotting to happen as well. And this is where we're going to introduce par eval. So par eval, slide right down here. So par eval is 2 for loops. Again, it doesn't have to be, but certainly we need at least, I mean, you don't even need a for loop to run par eval. Par eval just simply says, run this task on a worker and let me do anything else I want in MATLAB. So in this example, I'm using a for loop, but we could strip this down. So all we said was par eval, my code, and just go off and launch it and let me do other things in MATLAB in the meantime, okay? In this case, we're saying for I equals 1 to 100, we want to run 100 tasks. And then once it's finished, I'm actually going to run some other code. I can run anything because this is not blocking MATLAB. And then only once we've gotten to this point where we're now going to fetch each future, we're going to get our value Y and our lookup value of X. So that way we know how to plot this. Okay. So I'm going to run this, and then I have a question about how I wrote something, and maybe you already see what I'm going to ask. So I'm going to go ahead and run this, and I'm going to run this section here. And this is unfortunately where, yeah, we don't actually see the plotting until the very end. It's just the way LiveScript works. But notice that I was able to submit these tasks. I could call some other MATLAB code, and then I could get the plotting at a later time. So here's my question. What am I doing on line 33? Why does it say for IDX equals 100 decremented by 1 to 1? What am I will tell you, it actually has nothing to do with parallelization. Has something to do with, in the beginning, in the morning section, I was talking about, or earlier this morning, I was talking about some of the techniques to speed up MATLAB code. What am I doing?
Yeah, you're just pre-allocating. Your first thing you're assigning to the hundredth element, so it will allocate to the size of 100, and then it doesn't have to allocate. That's
right, exactly. So this is a poor man or a rich man's way of pre-allocation, right? So rather than pre-allocating using ones, nans, or whatever, what I've done is I've said, I want to take the 100th element, I want to create a future, and now that makes all of the Fs to be an array of futures. So it's simply just pre-allocating F of IDX, or pre-allocating F. So great, good job. So here you can see that we have parallelization without using par 4, but we're still using a parallel pool, right? So that doesn't go away, but we're using a par eval so that we can submit these futures, do other things, and then at some point later, fetch the results. And again, what I could have added in here is saying, well, you know, I've reached some tolerance or some limit, and I could have, if I wanted to, I could have terminated here. You know, that's just not how I wrote the example and so forth. So, okay. Any questions on par eval? Yes.
Yeah. How do you actually terminate it?
Okay. Yep. Good question. So what I'm going to do is I'm going to say F equals par eval. Hold on. Sorry. Let me do this in Here. So I could say f equals par f eval at well, I guess I should, well, just imagine, you know, my code, and it has maybe no, you know what? Let's do a live demo, right? All right, what's possibly could happen? So function, oh, what am I doing? So function, listen to me, and here it's just going to say while true, r equals rand. So we're going to just listen to, you know, maybe I'm inputting it from some data acquisition board, and I've got a bunch of data that's coming in, and then I'll save it as listen to me and save it. Really? Okay. And now what I'm going to do is I'm going to say f equals par f eval, my function, right? Listen to me. It has no input arguments, and that is it. So right now it's running. Should be, yep. So it's just running, right? So this is I've launched some task, and at some point maybe I want to get the results, or whatever. In this case, there's nothing that's coming back, and so it's still running. And now what I can do is I can f cancel, and then get the state, and it's finished. Yeah. So that would be one way to cancel it. You know. So again, this is not about running a for loop. I could just go off, launch some asynchronous task. Once I'm done with this, client server listening, whatever, I could then just say, okay, I'm done. Shut everything down. Cancel my task, and I'm finished. So. Good.
Okay, so if I can just ask,
no.
If you find the needle in the 10th iteration and you have million iterations,
yes.
So you have to manually cancel all these million iterations?
You would if you didn't use vectorization. So instead, what I can do is I can just say f.cancel. So I don't have to say f9, f12, f30. I can just say f.cancel, and it will cancel all my futures. So. But then it makes sound like my future is bleak. I don't want to cancel my future. So I just okay. So let's
just show this code a little bit, not just because it's hidden. Not just resize this window so it's this editor to see all whole code.
Sure. Let me run it again for you. Okay. So I'm going to create a future. And so now this listener is going off, running in the background. I can run other things. I can get the state of the future. It says that it's still running. So actually, that's something else I think I can do. I could. So here. I'm going to pause for 10 seconds, and then this more work is done. Let me cancel. I feel like I'm pressing my luck for what I'm about to show you, but so I'm going to submit a future. And now every 10 seconds, it's going to display something. I probably should have done a little shorter than that. Let's see if it's, yep. So you could, you can run your task on some other process, some other worker, and you could, whatever it writes to, you could get the diary from and so forth. So, all right. All right. Time to say goodbye to the future. Good. All right. I'd love to say that everything just works perfectly. This last example that I'm going to go through is going to highlight two different scenarios where, and is sort of explains why I say that we're going to rewrite your for loop as a par 4. So to begin with, we know now that if in fact we want to run our code in parallel, they have to be separate tasks. I can't have this iteration depending on this because this is dependent on this and this is dependent on this, and they're not talking to each other. So the code analyzer will already tell you something like this is not feasible. So you might look at this and say, well, Raymond, this actually is exactly what my code looks like. I have these interdependencies, or I'm dependent on previous iterations. Does that mean that there's no point in parallelizing my code? And so what I would say is, ideally, you'd like to take your for loop and get it to run X times faster. But all we're talking about is working with one data set, right? What if you have access to Carolina, where you have access to hundreds, if not thousands of cores? And so rather than working on one data set locally, you could work on 10 data sets, right? So not only does your for loop run, for, say, from 10 hours to 1 hour, but I'm working on not only one data set, but maybe 50 data sets, right? So that would be the ideal parallelization, right? Where you speed up your for loop and you're running more data sets in that same amount of time. In this example here, even though I can't speed this code up, this is one data set. So what I would imagine is I would take this code. This is still going to take 5 hours to run. I can't get this to run any faster, but I've got 50 or 100 data sets. And so my parallelization is now for I equals 1 to the number of data sets run this code, okay? All right, so always keep in mind that the tasks have to be independent of each other. I mentioned to you already that that the loop variable has to be monotonically increasing. The reason has more to do with if I wrote a regular for loop, we know that we can't index into A using 0.5, right? That doesn't make sense. For whatever reasons, when we wrote the MATLAB parallel language, we really wanted to put these bumper rails out, and we say that, well, you know what, we don't exactly know why you're going to use the loop variable, but I can tell you, you can't use it for indexing into a variable. And so therefore, you have to, well, you could use it for indexing into a variable. And so therefore, we have to make sure that you don't use step sizes like, 0.1, 0.5, et cetera. So that's the first thing. The second thing is that you cannot have nested par 4s. And folks will come up and say, well, okay, if I can run this par 4 10 times faster, what if I have an outer par 4? Can I run that 10 times faster and get 100 times speed improvement? Why will that not work? First of all, it's possible that you don't have that many workers to begin with. And so now all the workers are being consumed and so forth. But it actually goes back to the original tenet, which is that workers don't talk to workers. Very antisocial. So if a worker has started up a pool of tasks, then the first thing it cannot do is then talk to another worker that says, here, I want you to run some tasks and so forth. All right. And then we've already mentioned that we can't have interdependencies and so forth. In this, okay, so let's take a look at this next example. Again, we're going to work on this together. It's par 4 underscore conversions. So we already know then that the code analyzer will identify what parts of code will be an issue. And I will tell you, because we don't have a parallel debugger, it's very important that you pay attention to the code analyzer. I'm going to skip over the second example because what's really interesting is how do we deal with nested par 4 loops, right? Let me, okay, so let's take as an example this code right here. So in this example, if you can only parallelize one of these for loops, who thinks that they would parallelize IDX, and who would do JDX? So who would parallelize IDX? Okay, so one would parallelize the outer for loop, so everyone else would parallelize the inner for loop, the JDX. All right, so as a rule of thumb, you want to give each worker as much work as possible, because we're taking time sending all the code and the data to each one of the workers. You want to give it as much work as possible. So in this example here, I would parallelize for IDX, par 4 IDX equals 1 to n, and then give each worker the JDX portion of the work. The only time that I would parallelize the inner for loop is if the outer for loop only had a very few number of iterations. So imagine that I've got only 2 data sets that I want to process, right? Or we'll do this again. I'll take this back to North America. So we've got Canada, the US, and Mexico. And maybe I want to go and again do some census data on all the cities or the territories, et cetera, in each of the countries. So I could say, I could write a parallel for loop for I equals 1 to 3, because there's 3 countries. And then I could have each worker process 1 country at a time, right? But each country has hundreds, if not thousands, of towns and cities and so forth. So what I'm probably better off doing is saying for I equals 1 to 3, and now I'm going to give each country all the workers. So now all the workers are going to work on each country. It finishes, and then I go on to the next one. So it's on a case-by-case basis. I do agree that I would parallelize the outer for loop unless it was just very obvious that I've got access to hundreds, if not thousands of cores, and my outer for loop is only iterating, 2, 3, 4, 5 times, whatever the case is, so. All right. I want to wrap up at 12. So I'm going to show this one last example. Oh, yes, question. Yes, sorry.
Can you please give that the previous page?
Yep.
And what about Cartesian product of IDX and JDX and make it in one loop?
Yep. Okay. So good observation. So one consideration is that you flatten the for loop. So rather than having doubly nested for loops, that you just have one. And in that case, that would be a good solution as well, right? So you just say, I'm going to almost run it serially and just have one for loop. And that would certainly be an option. So good catch. Good catch. Yeah. All right. Let me also just highlight tick bytes and talk bytes. This is a development tool that you can use to understand how much data is being sent back and forth from the client to the workers and so forth. So take a look at tick bytes and talk bytes, and that will help explain how much data is being sent from the client to the workers and so forth. So that's a helpful utility function. Okay. Here's, this will be the last example we do this morning. That's not one. Oh, refactor. Okay. Okay, so the reason I like this example is it helps illustrate the way MATLAB is thinking when it's running your code. We've got a loop for I equals 1 to 4. We're going to we're going to load a mat file called xy.mat. We're going to assign z equals to x times y times rand, and then we're going to save a mat file z1.mat, z2.mat, and so forth. And the variable z is going to be stored in the mat file. Okay, pretty straightforward. All right, so let's go ahead and rewrite this as a par 4. And what I'd like to hear is what happens when we do that. So rewrite it to be par 4, and then go ahead and run it, and then tell me what happens. All right. So I'm going to run this section right here. And the first thing that should have told us something's going to be wrong is that the code analyzer identified load and save, right? All right. Again, the body of this code is being run on a different worker. Actually, let's say we've got 2 workers, a par pool of 2, and we've got 4 iterations. So each worker is going to run this code right here. When MATLAB runs the code, it statically analyzes the for loop and figures out what functions and variables need to be on each one of the workers. So I'd like for you to think of this code actually being lifted and being run on a completely different machine. So if it can do that, then we can run the code. So in order to do that, it has to have access to xy.mat, okay? It's going to create z. We're going to use IDX, but that's the loop variable. That's fine. Where's it getting x and y from? Where's x and y coming from? The workspace. Okay. Yeah. Maybe. Any other guesses where it's probably coming from? xy.mat, right? Okay. So when you look at the code, you say, well, this is pretty straightforward, right? X and Y are coming from xy.mat. That's not how MATLAB sees it, okay? What if I wrote the code this way? So would anyone look at this code and say that F1 and A45 necessarily come from this thing called triangle.mat? No, right? I mean, maybe, but I think you have a better chance that it was actually in the workspace than from this, right? So MATLAB doesn't read the mat file and say, oh, that's where it's coming from. So when MATLAB runs, analyzes this code, it has to determine what types of tokens each one of these things are: Z, IDX, rand. And if it doesn't know what the token is, it has to either be a function or a variable. And if it doesn't know what it is, it assumes it's a function. It just says, I don't know what F1 and A45 are. They must be functions, and we will resolve that when we run the code on the workers. It's probably on the workers' path somewhere. So then MATLAB goes to run the code, and when we load xy.mat, all of a sudden magically appears the variables x and y, and that creates an issue because when MATLAB runs the code and says it's one thing and it becomes something else, that's an issue. And so there's this notion of transparency of variables. That is, we cannot dynamically create variables on the fly. So how are we going to work around this? So instead, one option is I'm going to create a variable z xy.mat. And now I'm going to reference d.x and d.y, okay? I'm going to show you this example first because it is certainly one way of doing it, but it's not how I would do it. And I'll explain why. But this is certainly a valid option, right? What we're doing is we're not introducing new variable z, MATLAB sees the code, says, oh, z is a variable, it's the output of calling load. And when you call the functional form of load, the output argument is a struct whose field elements are all the variables that you loaded from calling from calling load. So now d.x and d.y exist. Why am I not a fan of this? So when you go and modify, and now you can start to see why I'm using the term refactoring. When you refactor your code, one of the first things I'll do is take my par4 and I'll rewrite it. I'll convert it back to a for loop, make sure I haven't created any discrepancies or things that don't work for whatever reason in a for loop. Okay, so this is a good practice. But if you were to write this code, I mean, nobody would write code this way, right? So you might even ask, well, why are you calling load in here to begin with, right? I mean, wouldn't you call it outside? So who can tell me a good reason why you would call load inside the par4 and not outside the for loop? Okay. I'm going to tell you that xy.mat is actually half a terabyte. Do you want to load half a terabyte onto your local machine and push it down that pipe that's going to all these workers? Or are you willing to take the overhead of having each worker do the exact same task, but on a machine like Carolina, where you have a lot more memory and a lot more CPU cycles and so forth? So now you start thinking, now you start to get the sense of what it is to be a MATLAB parallel programmer. The things that you would do naturally in MATLAB writing serial code is not necessarily the best way to do it when you're writing parallel code, okay? So how would I address this? What I would do instead is I would refactor this code entirely. So that it's down to almost what I call a unit of work. A unit of work says that for MATLAB, I'm going to take this code, 50, 100 lines of a parallel for loop, a for loop, and I'm going to compress it down to a subfunction and let the worker just operate on that. The MATLAB client doesn't know anything about how it works. We just rewrite it as a subfunction. And then now when we run this code, now I can call load and save as I normally do. It's perfectly fine, right? And the reason I bring up this example to finish the morning session is that refactoring the code is probably going to be one of your best options when you write a for loop or rewrite it to be a par4. The examples that I've been showing you this morning are very contrived, very simple, and they all work really well. But the reality is that your for loops are going to be substantially longer, much more complex. There's things I haven't even dived into. This is an introduction to parallelization. That you will realize very quickly when you start to do this. And one of the best pieces of advice I can give you is that if you're able to refactor your code and just press it down into a single subfunction, the shorter your parallel for loop is, the better off this is going to work. I'm going to finish off with just explaining save. The reason save also has a problem is because it needs to know something about the base workspace. When you save a variable, it's looking at the entire base workspace. But in that parallel for loop, it's running save on the workers, but it has to communicate back to the MATLAB client and look at the base workspace and say, give me all the variables that are in the base workspace. The workers do not talk to the client. I know we talked about data queue, but that's not what I'm talking about here. Everything happens from the client to the workers. So the client sends the code, the client sends the instructions, the data, et cetera, and makes the requests. The workers cannot request back to the client saying, hey, I'm calling save. Tell me everything that's in your caller's workspace. When we compress this down to a function, because this is now a function, the only workspace that it sees is the function's workspace. It doesn't look at the caller's workspace, so it doesn't need anything there. So, okay. All right. So I know we covered a lot. Look at that, 12 o'clock, right on the nose. Perfect. Because I don't want to be making you guys late for lunch. So we will be around for lunch. When we come back this afternoon, we're going to talk everything about, now that we understand something about parallelization, how do we get anything that we're talking about today and running on the Carolina cluster, okay? So thank you for your time. For those who are not going to be joining us in the afternoon. We will be sending out shortly a lot of information. First of all, you'll have links as of a PDF of the slides. You'll have a link to the audio or the recorded session for this morning, as well as this afternoon. We'll record but I certainly encourage you to be here this afternoon. We have fantastic prizes. Have I shown you all the things we're giving away? You can only do that if you're here. And then we will provide a questionnaire. We'd ask you to, please provide some feedback so that we can improve the workshop. So you'll have slides, you'll have the workshop examples, you'll have the audio, video, and you'll have a questionnaire. And all of that will be provided to you in a couple of days. And then the last thing that we'll also provide is we've been monitoring the Zoom chat. We'll compress all the questions into a set of answers, and that will get posted as well. So, okay. The last thing before we wrap up, for this afternoon session, it is important that everyone has an account on Carolina, as well as having a VPN access to Carolina. And then we're going to do that. We need that rather, because we're going to use the Carolina On Demand interface to the cluster. It's much more user-friendly. In theory, you can do everything that we're going to do just using an SSH terminal session, but I'd really encourage folks to take the time to get a VPN client configured. If you don't, I'm going to ask the MathWorks folks to post in the Zoom chat. The very first link to the VPN is already, if you could just repost, if you don't mind, Shubo. Shubo's going to post in the Zoom chat a link to the VPN instructions. The staff are here, so if anyone does have any questions before we resume at 1 o'clock, I'm sure they'll be happy to help however they can. But none of this is possible without an account on Carolina. So is it safe to assume that, is there anyone who does not have an account on Carolina? Great, everyone has it. And then I'll assume that you have VPN access, or if not, the link that we send out will help answer all the questions. So, okay, with that, we'll conclude, we'll finish, we're wrapped up, and we'll see you at 1 o'clock for part 2 of the workshop. All right. Good. Yep. I hope everyone enjoyed their lunch. It's great to see everyone comes back. Before we start with the second part of today's workshop, any questions from this morning? And certainly there's a lot that is thrown at you. And any questions on PAR pool, PAR 4, PAR FEVAL, data queue, tips and tricks or anything? Again, we're going to break at 2:30. I'm happy to be available to answer any questions, but anything come to mind now? No? All right. So this afternoon, we're going to switch gears and we're going to learn how to run MATLAB on Carolina. I took a quick survey this morning, but as a reminder, there are some folks who have worked on Carolina before. Yep, just one. Okay. All right. No, fine. Good. And have you run MATLAB on Carolina? Okay. Only your code. Okay. All right. So that's what we're going to talk about this afternoon is how do we connect to the cluster and how do we run MATLAB on it. We're going to be using Open On Demand. Sir, have you used Open On Demand on Carolina? No? Okay. Yeah. BNC. Okay. All right. So we're going to show a new way of doing it, or let's just say a different way. It might be a good fit for what you're doing. So, all right. So everything's going to be about using MATLAB Parallel Server. Just to sort of get the name out of the way, really, it's MATLAB Server is a product. All things that you need are already installed on the cluster. So you don't need to install anything. There's a little configuration that you have to do. And we're going to walk everyone through how to do that. But really, MATLAB Parallel Server is a product that allows you to run multiple MATLAB instances across multiple nodes. But in itself, it is just MATLAB. It is not, in fact, a server product. All right, let's just jump right into it. We're going to talk about how to connect to the cluster. We're going to talk about how to launch MATLAB. One of the first things that we're going to do is we're going to run a local pool on Carolina, just so you sort of get familiar with what we were doing this morning using MATLAB Online. Now we're going to use MATLAB on Carolina. And then we'll talk about how you can run multi-node jobs and so forth. So the thing that I want to mention right now is that this is all going to be about process, not performance. And what I mean by that is that now that we start talking about supercomputing center or supercomputing clusters, you have access to hundreds, if not thousands of cores. This afternoon's lecture is not about how I'm going to show you to run a 1,000-way job. In fact, the jobs that I submit are going to be quite small. It's more understanding how do we get connected to the cluster and run jobs? How do we fetch results and so forth. There's, for those who have not used Carolina before, we have documentation. Just as a reminder, however, I did ask in the morning, everyone has access to Carolina. Does everyone now have access to the VPN client? Is there anyone who does not have the VPN client? One? Two? Okay, so here's what I'm going to ask. Shubo, if you could post.
Sorry.
Okay, so if you could post in the Zoom chat the link to the VPN client, and then if you could follow along with the instructions, it's downloading the VPN client and then configuring it. The screenshots explain everything about what to do. I don't see IT staff here at the moment. Is there anybody from the IT staff? If there's any question, one. Okay, thank you. Okay, so if anyone does run into issues with the VPN client, just raise your hand or put something in Zoom, and Shubo can let me know. And
so there's someone on Zoom who says, I don't have it, but SSH works fine.
So the reason that we're going to use the VPN client is because that's what's required in order to use Open On Demand. The concepts that I'm going to cover this afternoon certainly can be done actually from just a terminal window. So if that's what you choose, that's fine as well too. So, all right. The next thing is Shubo, I don't know, did I give you that link? Do you mind? Thank you. Appreciate it. Okay. So the second link here is to a user guide that we've written that walks people through exactly what we're going to be covering this afternoon. So you will have a PDF of these slides, and I'd say these slides are more exhaustive, but the user guide is a good sort of getting started guide. It is a hybrid between our parallel computing documentation and the Carolina documentation. So it supplements them, but it certainly does not replace them. But everything that we're going to be doing in the first 5 to 10 slides or so is covered in that user guide. So, but that is certainly a good starting point if you need to. As I mentioned, you have to have an account on Carolina, and it's advisable that you have a VPN client because, in my experience, that's required for Open On Demand. So, Shubo, you have the link. Thank you. Yep, great. All right, so I've been mentioning about on demand. Open On Demand is a web interface to an HPC system that was devised by an NFS grant in the States, comprising of a multitude of universities, most notably Ohio Supercomputing. We see it a lot in the States, but we're seeing a growing number in Europe as well. From my perspective, you can use it. You don't have to, but I think it's pretty good. I mean, it works well. And the reason that I think it's useful is because if you're not familiar with Linux, if you're not familiar with VI or Slurm or any of these other components, it's a nice way of being able to just graphically request the things that you need and then simply launch MATLAB. And it's, but at the end of the day, it's a VNC server, So the way I'm going to show this afternoon technically is not the way, it's not the only, certainly not the only way to do it, but I would recommend doing it. So I'm going to give a brief introduction into Carolina On Demand. I'll talk about how you're going to log into it, just some basic navigation. How do I get files onto the cluster? How do I run MATLAB? How do I get files off of the cluster, right? So now we have to start thinking about rehosting your code, because what we're going to be doing this afternoon is showing you how to connect to the cluster and run MATLAB there. That means that all the files, the data, et cetera, have to be on the cluster. This is a workflow that I call on-prem submission, right? What's feasible, although we're not going to show it today, is remote submission. So in practice, what we could do is we could, from your laptop, submit jobs to the cluster as well. And if that's something of interest, when you fill in the evaluation at the end of the day, I'd encourage you to ask for this, and we can certainly walk you through how to do that. And we're just starting this partnership with IT for Innovations. So we're looking for any feedback of things that you would like to see happen. So remote submission, that is submitting from your machine to the cluster, is something that we could stand up quite easily. But today we're just going to be doing everything on the cluster. So for that reason, you have to know how to get access, how to get your files up there and so forth. So what I'm going to ask everyone to do is to, and let me just take down a note here. I'd like everyone to VPN into the cluster. So let me, I realized I sort of skipped over adding that as a slide. So I'm going to, okay, so I will walk folks through how to do this. The VPN client is called should come back. Okay, good. So the name of the VPN client is, if I'm saying it correct, Forti client. I apologize. So this would have been in the instructions that for the link that Shubo sent a moment ago. In order to connect to it, do this hopefully without breaking my connection. Yeah, I apologize. I will include in the slides the step-by-step instructions, but it is in the link that that was just posted. So why doesn't everyone take a moment to VPN in, and then we'll connect to Carolina. So in essence, once you bring up the VPN client, you're going to want to specify the gateway. So reconnect.it4i.cz. You're going to use 443. That's fine. And then everything else, you can supply your username so you don't have to supply it later. You'll save that and then connect. So were folks able to VPN in? Is everyone? Yep. Okay, good. All right. So with that, the next thing that we're going to do is we're going to connect to on demand. Okay. So, and I don't think anyone's used this before, right? So, okay. All right. So let's give it a little tour of how we use this. Using Carolina on demand, you can click under Files to your home directory. And this is this has drag and drop capabilities, so I can create a file, drag it in. So let me. I won't be able to do it. Okay, I'll just show it in the slides. So you can create a file on your local machine, drag it into the browser, and then upload the file. So this is how you're going to get files from your machine to the cluster. Likewise, once the files have been generated, you can click on the ellipse and download the files to your local machine. All right. Now, in order to run MATLAB, what we need to first do is create a terminal session. So I'd like you to go to interactive apps. So let me I'll start from over here. So interactive apps, and the one that I always pick is Carolina Login Mate. All right. So go ahead, so once you're logged into on demand, click under interactive apps, and then Carolina Login Mate. So Carolina On Demand has recently been rolled out. I believe my understanding is that apps will be added to this. So, for instance, there's a MATLAB app that we could add to this, and we'll talk to the team some other. Right now, it's not feasible, but maybe perhaps in time. So what we're going to do instead of just launching MATLAB from On Demand is that we're going to bring up a terminal session. So I'd like you to, the only thing that you have to provide is the number of hours that we're going to run this for. Let's just say 4 hours just to be safe. I assure you we'll be out well before then. You're going to select the number of hours and then click launch. Now, what's happening right now is that Carolina On Demand is generating a Slurm job script. It's Slurm because that's the scheduler that's being run right now. And this is now going to go off and give you a dedicated node on this machine. This machine has 128 cores plus, Mate, any sense of how much memory per node? Rough? Okay. So, yeah. All right. So, yes.
As far as I know, it's just the terminal or DVNC on the login node. You have to then request to the compute node.
You're right. Thank you. I'm sorry. I'm getting ahead of myself. Yeah. Good catch. Good catch. Yeah. So this is getting you onto the login node. From here, we're going to launch a job. Thank you. All right. So this gets us onto a terminal window, a login node. And from here, we'll launch MATLAB. So I have a couple of sessions that are running right now, which is why you see this. You should see only one session. The one that, let's see, this one's got just under 4 hours. Okay, good. And this one has three. Okay, all right. So let's take a look at what's been displayed here. I have spoken with Ohio Supercomputing, and if it works, they suggest the highest compression and the highest image quality. So my experience, and this is going back to actually being in the US while using this, that this has performed well. So I would suggest sliding all the way to the right. And then from here, we're simply going to click Launch Carolina Login Mate. Okay. We can see that we'll have this terminal session for just under 4 hours. And so I'd like to wait until everyone gets to this point before we continue, because now I'll show you how we can launch MATLAB from here. So just a thumbs up once you've gotten to this point here. Yep, good. 1, 2, 3, 4, 5. Yep.
I just have a quick question.
Yes.
The compression image quality that relates only to the display of the desktop, right? The virtual desktop.
Yep,
right.
That's right. Yeah,
just to be sure.
Graphics.
Thanks.
Yep, yeah, good. Okay, so for those of you who use Windows operating system, this, of course, will probably look quite different, maybe even a little daunting. We'll keep it as simple as we can. If you're used to Linux or use a Mac OS, then this probably looks, well, Mac, this will look a little bit more familiar. But again, this would be an advantage that if we can just launch a MATLAB app, we don't even have to worry about this next step. But all right, so how are we going to, from here, launch MATLAB? Well, let me, yeah, okay. So what I'm going to ask you to do, well, the easiest way probably is just clicking on this this window right here, this what looks like a television screen, and that's all we have to do. Okay, so I'll show you one more time. I'm going to close this. If you just click on, I'm going to assume everyone has this icon up at the top. If not, another way to do it is if you right-click on the desktop and click Open in Terminal. And in the slides, that's the way I show you, because I don't know what folks have for their terminal, but either click on the screen to bring up a terminal window, or click right click anywhere on the desktop and click open in terminal. Right. So either one is perfectly fine. Okay, so there we are. Now, if you're using Windows or a Mac, typically you install software, and then you have shortcuts on your desktop to be able to get to it. For Linux, it works in quite different. There's really nothing on your path, your system path, and instead we need to add MATLAB to your path to be able to get access to it. So that's the first thing. The second thing is that we got to figure out where we're going to run MATLAB. Now, what we've done is we've simply gained access to what we call the login node, or sometimes referred to as a head node or submission node. Those can be interchangeable, but really what it is that it's on this sort of are you familiar with this cluster? So does it have it has a load balancer and there's multiple head nodes, or is there just one? There's 4. Yeah. Okay. So you're going to be when we launch onto the cluster or the head node, there's one of 4 machines that you're probably on, but these machines typically do not have a lot of memory, a lot of cores. They're not designed necessarily to run MATLAB. Certainly not run MATLAB the way you think of doing it, which is sometimes for hours, if not days at a time. It's designed, this machine or these 4 machines are designed for compiling code and submitting jobs to the cluster. Okay, so right up to this point, you've been running MATLAB or anything on your own local laptop. You own all the resources. You're not contending with anyone else. You are now getting into this sort of stratosphere where many people are using the resources that you're going to be using this afternoon. So the login node is only for submitting jobs to the scheduler, and then the scheduler is responsible for going out and allocating resources and running your job. In this case, your job is just running the MATLAB client. We're not even talking about parallelization right now. All we're simply doing is, how do we get connected to the cluster, and how do we get onto a dedicated machine so that we can run MATLAB on that machine? Okay. All right. So pictorially, you're thinking that you're on your laptop. From the laptop, you're now connecting to Carolina On Demand, which routes you to one of 4, almost, it's not a good example, but almost think of it like 4 Chromebooks. It's just sort of a lightweight interface that really then is responsible for getting access to the back end of nodes, which is called the compute nodes or the execution host. This is where you tend to have a lot more cores, a lot more memory, and so forth. All right. So to do that, we have to allocate a resource. Okay. And so, Shubo, can you post the first salloc, this command right here? Okay. All right.
Just some of the folks online are saying that the 40 VPN is taking quite a lot of time to install, and they're asking if there are other VPN clients.
Nope.
Well,
nope.
Okay. Yeah, it's supposed to know.
The question is that, like, for preparation, we asked to install SSH and SSH key, etc., but we don't ask to install this 40 client, and I wondered why install it now.
So my understanding is that was a precursor to today's class.
I suppose not, because I done everything. There was another precursor, not this one.
I'm sorry, I'm not understanding the question. One more time, please.
In homework, in precourse work, we asked to install SSH and SSH key and etc. to access to Carolina, and we did that, but not this VPN client. Can we access with the terminal, just as it's simple SSH terminal, instead of installing
yes.
something?
Yep.
Okay.
So if you don't want to use Open On Demand, or if you're having issues installing the VPN client, You can SSH to the to Carolina. I'll show you how to do that.
Yeah, I know, no problem. I got it. I know, not sure. Okay, and can type. I can type the same that you now. Yeah. Okay.
Okay. Yes. Yep. Yeah. So as long as you can get onto the login node, the only thing that I would mention is that you need to have a VNC server running in order to run SSH with X forwarding. Okay. But
yes, fine.
What I'll do, if you can't run MATLAB if you cannot run MATLAB graphically, I'm going to provide in the chat a workaround at the appropriate time. So, is there anyone else online who does not or who doesn't have access to the VPN client or up to this point? Okay. So if anyone is looking for instructions to how to SSH to the machine, I will provide that now. So what you can do is SSH. I believe I don't say meta here, but that you have to specify your private key and then your username, and then it's simply carolina.it for i.cz. Okay. All right. With that, let's keep going. So yeah. Actually, this is the main thing that you have to do. So what you should do is say just SSH user ID at carolina.it or i.cz. Yeah. Okay, I'll leave that there for a second. Okay. Good. Now, I believe this has been now posted in the chat. Let me explain what we're doing here. We are on the login node, and we're asking for an allocation on one of the compute nodes. salloc is a Slurm command. Again, Slurm is the scheduler that has been installed and is used on Carolina. And then the -A is the budget name that is being used, and everyone should use that budget. So everyone should be a part of this budget because you're a part of the training today. And if you use a different budget name, then you won't be associated with the reservation. The reservation is so that you can jump the queue for today. When you submit a job, you are in line with everyone else. And when your job gets to the top of the queue, then that's when your job will actually run. Because we're running a dedicated workshop today and we don't want to spend time sitting in the queue, the staff have been gracious enough to provide us a reservation so that we can hasten that process. But it's important that you provide this entire name. So, all right. Once you have done that, you should then get the terminal window to come back once it says that the nodes are ready for the job. My prompt, whether it's login 1 or bash 4, is immaterial. Your login may look your system prompt may look a little different. That's not what's important. But at this point now, has everyone been able to connect to a submission? A compute node. All right. So there we are. We're on a compute node. Now, there's a lot that went behind this command, things that you're not even aware of, like How many cores do we get? How much memory do we have on this machine? How long can we run on this? Can we run on this for now the next 10 days? That's not the case. Do we have access to GPUs? All of these things are configurable in this call to salloc. Today's workshop is not about Slurm. So my suggestion is that you follow up with the IT4I staff, and I'm sure that they provide documentation that explains all about how to configure your Slurm jobs. I'm going to keep it as minimal as possible, right? So the next thing that you need to be able to do, is launch MATLAB. So, no, hold on. Okay. So we've gotten to this point. Before we launch MATLAB, I'm going to ask everyone to copy the workshop files over. So this morning, we got the workshop files from my MATLAB drive. This afternoon, we're going to get the workshop files from a central location that we all have access to, okay? Shubo, if you could throw in, yep, great. Okay, so at the bottom here, you can see the command that you're going to run, but it's listed right here. So you're simply going to, from your Unix prompt, type the letters starting with a /MNT. And Shubo is posting it into the chat. So I would suggest just copy and paste that right from your terminal window. And thumbs up once you get to the word done. Thumbs up, good. Thumbs up, good. Who would like a little bit more time? A little more time? Because we're going to use this for our work. Yep, more. That's fine. That's fine. Yeah, thumbs up. Good. Okay, great. All right. Raise a hand if you need a little more time. A little more time. No, yeah, good. You're done? Okay, great. You guys good? Good. All right. You're good? No? No, you. Yeah, you in the back. No? Not good? All right. All right. So now the last step is that we're going to add MATLAB to our path. Again, when you start up an X-terminal session like this, it's pretty bare bones. It's designed that way because sometimes one application can clash with another application, or it can bog or slow things down. So the way Linux typically designed is we keep it as minimal as possible, and you opt in for whatever packages or applications you want to run. So to add MATLAB to your path, we're going to use what's referred to as a modular system. Shubo, if you can copy and paste the next two. So we're going to, what I have here is just a comment when there's like that hashtag, so that you don't have to enter that. What you do need to add is the modular load MATLAB and then /R2023B. Okay, so we're using the latest version of MATLAB on Carolina. Was it a question, sir? Oh, sorry. The gentleman right here, if you don't mind. Thank you. All right, so we're going to add MATLAB to our path. And then in order to actually run MATLAB, you're then just going to simply type MATLAB, all lowercase letters, and then you can hit the Enter key. And when you hit the Enter key after that, you should see the desktop appear, and a desktop environment that looks quite familiar with what you've used in the past. And really, from that point on, everything should look familiar in MATLAB. Okay, so modular load MATLAB And then it's not necessary, but for the time being, we're going to specify the version so we know which version of MATLAB we're running, right? In fact, if I were to type, you don't have to do this, but if you were to type which MATLAB, you could see that MATLAB has been installed in a very particular location. All right, we're now ready to run MATLAB. All right, thumbs up when you get to this far. Thumbs up, thumbs up, thumbs ups. Okay, that was a hand. Hold on. Yeah. Oh, no. Yeah. All right. Shubo, we're good. Sounds good. Yep. Okay, good. All right, so there we are. Okay, it took us a little time to get here, but let's just review what we did. We VPN'd into the network. We started Carolina on demand. We launched a login session. We then allocated a resource on a compute node, which you happen to own this entire node. And then we added MATLAB to our system path, and we launched MATLAB. All right, good. So the first thing that I'm interested in doing is, can we run just a local pool on our machine, right? I mean, that's what we learned this morning. So why don't we make that to be the first thing that we do now? So let's start up a local pool. And what we're going to do, instead of just specifying a number, we're also going to specify the term local. Okay. So I'd like you to type par pool local. And then the number 4, okay? Because this machine has so many cores, we want to certainly specify how many workers that we want to start up, right? So just for simplicity perspective, now these workers are starting up on the cluster on the same machine that MATLAB is running. That's why we use the term local. Local is local to where the MATLAB desktop is running, okay? So these are not running on your machine. These are running on the compute node that you're running, the MATLAB client. And there we are. We have this, okay? So thumbs up once you get to this point. Connected 1, 2, 3, 4, 5, 6, 7. Okay, good. We'll give it another second. This usually can take about 30 to 45 seconds, you know? So it's not, it might not start up instantaneously. That's fine. Yeah, good. All right. So now that this pool is working, what can we do with it? Well, again, these examples are going to be very simple. It's designed this way, but let's just run par 4, IDX equals 1 to, let's say, 8. We're going to pause for 3 seconds and talk. Okay, so I'm going to just put this all in one line. We're going to time how long it takes to run par 4, IDX equals 1 to 8. And we're going to pause, for 3 seconds. So if I ran this serially, right, this would take 24 seconds to run. But instead, this should take about 6 seconds to run, right? We think this is going to take more than 6 seconds. 7, 8 seconds? 6.5 seconds. That doesn't really make sense, right? Why would it take 6.6 seconds to run something that should have only taken 6 seconds to run? And why am I showing you that? Okay, so let's think. There's a couple of things that are happening here. The first is that even though it happens magically, we are sending code, right? In this case, pause for 3 seconds or so, to those workers, right? So there's communication that's happening from your client to those workers, right? And then the second thing is that we have to warm up those workers. If we were to run this again, I'm going to say 6.21. Let's see. How close are we? Even faster. Okay, so what happens here is that MATLAB, the workers have cached that code, and so they're all warmed up. We ran the same code. It's like, okay, I know what to do. So it's not surprising that the second and subsequent times that the code will run perhaps a little faster. But I show you this because even that, it still wasn't 6 seconds, right? There's a little overhead of saying, hey, workers, I need you to do something. And I'll tell you what, you can't get a more simpler example than pause at 3, right? Like this is not going to run in 2.5 seconds, right? I mean, it's going to bring at least 3 seconds. And then there's 8 iterations and 4 workers. So, 6 would be the best you get. So this shows you, no matter what, there's always going to be a little overhead when you're submitting a job. All right, excellent. Now, we've I actually got a little ahead of myself. The things that we're going to focus on today is this afternoon, we're going to talk about running MATLAB jobs interactively using parpool, which we focused a lot in the afternoon, in the morning. I'm going to also introduce the MATLAB batch command, which is very similar actually to par feval, which allows you to submit jobs to the cluster and then quit MATLAB. And then we'll finish off writing our own Slurm scripts, because you don't always need to run MATLAB interactively like we're doing here. Okay, so the parallel pool we saw this morning, we can only run one parallel pool at a time. But sometimes we want to launch a bunch of different jobs. So the batch command is an asynchronous command, just like par feval. Excuse me. But the drawback to batch probably is that, much like when we were talking about par feval and we had to fetch and cancel and so forth, we'll have to use the MATLAB API when you're using the batch command. So, all right. So we've already jumped into the first example here. So now that we've got a basic understanding of how to submit a job or run a job locally, the question is how do we get MATLAB to be able to submit jobs to Carolina, right? So this is just running a local pool like we did this morning. There's really nothing new other than that. But what we want to be able to do now is leverage all the nodes, well, not all the nodes, but a lot of the nodes that we have on the cluster, right? And so to do that, we have to create a new profile for Carolina. And I mentioned this term profile a little bit earlier. A profile is a way for MATLAB to discover the cluster and provide instructions about how to submit a job to the cluster, how to get the state of a job, and how to be able to delete a job, okay? So MATLAB is going to be actually generating its own Slurm script for you, right? You don't need to know anything about Slurm, the scheduler. By simply launching MATLAB through OOD or through VNC, et cetera, MATLAB will automate that process for you. And you'll see by the end of today's session where there's a lot of value in using the batch command for that. But we have to first start off with a profile. So imagine that you've got a Word document and you want to take your document and send it to printer A, because printer A can print both black and white and color. But printer B can print on the front and the back, right? So these printers serve different purposes. And from the Word document, you simply send it to printer A, printer B, whatever the case is, right? There's nothing in the Word document that says anything about the printer. I want you to start thinking in the same terms that when you have MATLAB launched on a compute node, that you might say, I want to run something locally, or I want to run it on Carolina. There's also Barbara. That's another HPC cluster, I think, here. So you could even maybe submit it there, or maybe there's some other remote cluster, who knows where, right? And all from within your MATLAB environment, you can be able to submit jobs to any one of these clusters. But there's nothing in the code that says, oh, I'm running on Carolina, so do this, or I'm running local, do that, okay? So then the question is how are we going to teach MATLAB about Carolina, okay? And the way that we're going to do that is through the Discover cluster. So what I'd like you to do is go to the Home tab of MATLAB. So I'm going to go to the Home tab of MATLAB. And actually, if you have a pool that's running, I'd like you to pick your favorite way of shutting down that pool. Now, we know a couple of ways, right? We can use GCP. We can use the lower left-hand corner. However you want to delete the pool, but go ahead. I'm going to use delete GCP. And remember I said that GCP will start a pool if one hasn't already existed. I can force it to not create a new one by calling no create within the GCP function. So that's going to be my next way to do it. So I'm going to delete the current pool. And we can see that this is a no op. If I were to try to delete it again, it's simply, there's no harm, right? So if a pool is running, it will delete it. If it doesn't do anything. All right, so let's go ahead and actually I probably already, no, yeah, I do. Okay, so let me just delete that. Good. All right. So what I'd like you to do is go to the Home tab and then slide over, and you'll see those 3 boxes. Right next to it is the parallel menu item. And on the parallel menu item, I'm going to ask you to click Discover Clusters. Now, for those who are running MATLAB from a terminal window, is anyone running MATLAB just through like straight SSH and not running MATLAB graphically like this? Okay. Shubo, could you?
On the online, yes.
Okay.
Somebody is.
So for those folks that are running MATLAB in a terminal window, what I'd like you to do is call par cluster. Shubo, can you type that in there?
Yes.
Okay. So this is just for those who are running MATLAB in a terminal window. Go ahead and call par cluster, and you actually now will be slightly ahead of where I am. All right. So everyone has clicked Discover Cluster. You want to select, make sure the first one is selected and the second one is deselected. And what we're going to do is we're going to search the network for schedulers that are running on our network, and specifically Carolina. So I'm going to click Next. And hopefully everyone will see Carolina, and the host will happen to be the machine that you're running on. And then you can click Next. So does everyone get this line right here? Your host might be, okay, good, thumbs up, good. So the host is probably going to be, well, actually will be, because we're all on our own unique host. The name of the host is immaterial. So now I'm going to click Next, and it's going to ask me if I want to make this to be my default profile. I'm going to select yes. It makes it a little bit easier, but I'll also show you how you can change your default profile. And now I'm going to click Finish. And going back to the printer analogy, just like you have a default printer, we can have a default profile. And that just simply means that if I'm running any parallel code, it's going to default to that profile, to that cluster. And in this case, it means that everything, like when I run a local pool, or when I run a pool, if I don't specify to use a local profile, then it's going to always run on Carolina. So, Shubo, do you have a...
Sorry, what do you want me to do?
I see it's red. It's lit.
No.
Oh, okay. All right. Nope. Okay, that's fine. Okay, so thumbs up if everyone has a Carolina profile. And the way that you can tell is if we now go back to the parallel menu item and we click Select Parallel Environment, we'll see we have processes, threads, and now we have Carolina. It was auto-generated. And that is now our default. And we know it's the default because there's a check mark right next to it. And this is also how you can select some other profile to be the default. You can just select the profile with through this menu. So, but we're going to keep it as Carolina for now. Okay.
One question here. Is this setting, can we be persistent between MATLAB sessions?
Yes. So this, now that we've created a Carolina profile, it will persist with us because that information is stored in the home directory on the cluster. So this has no impact on your machine. Your machine will never see this because everything we're doing is on-prem, on the cluster. Okay. So the next time you log in, whether it's through VNC, Open on Demand, etc., all this has already been taken care of for you. Yes, we used a different budget name, but that's just an accounting perspective. It has nothing to do with your user ID. If your username changes, then yes, you have a different home directory, but that's for a different discussion. All right, so now what I want to do is I want to start a Carolina profile. And what I can do is type par pool, parenthesis, double quote or whatever. And if, okay, let me, I can start to type Carolina, and it will autocomplete for me. So, or you can type it in, it doesn't matter. Now, I do not suggest that you hit enter because this is going to start up a large pool. So let's start now a pool of 40 workers. Yes, sorry. Sorry, bear with me. I got ahead of myself. So what you need to do, we're going to type C equals par cluster, and there are a couple of tasks that we have to do. So for those who are using config cluster, the same is going to apply to you. Okay, so here's what I'd like you to do. Okay, so just like when we ran salloc earlier, we had to specify a budget name or project name rather. We also have to specify, because MATLAB is generating a script for you. And so you have to specify the project name. And then we're going to save that. And the other thing that we're going to do, let me go, is we're going to set the reservation as well. So let's do this one step at a time. So we'll type C equals par cluster of Carolina. And then we're going to set this project name. And I think, Shubo, I have this in the chat as well. It should be like right at the bottom.
One question. Project name is that you have on, or is or login name? What is that one? We have to write the same as you or own login name.
The project. You're asking about the project name?
Yes.
Yes. So we are all part of this project today. This is a director dedicated project for today's workshop. At the conclusion of today's workshop, we will unset this. And if you decide to use Carolina in the future, you will have to use your own dedicated project name under your, whoever your PI is, okay, or so forth. So everyone should use this project name. This way also, you're not using your allocation, you're using the workshop's allocation. So, okay. Okay, so in the Zoom chat, you should see the project. I mean, you should see this command, c.additional properties.project name equals, and this is the project that we should choose. Okay. Again, yeah, this is only for today's workshop. The other thing is that we want to specify the reservation, and so this will be also in the chat. Just copy and paste this, and then we're going to save the profile. So we created a Carolina profile, and I'll show you there are certain properties that we can change. These are just a couple of them, but it's the project name and the reservation. So, okay. All right, so I'm going to give folks a moment to do those two things. Let me go back to the previous one. So the first thing that you want to do is you want to set the project name to today's project. Okay. And you only have to save the profile once. You don't. I mean, you can paste that in if you want to, but so that's the first thing that we'll do. We'll set the project name, and then the second is we're going to set the reservation.
Raymond, can I ask a question for an attendee?
Sure, sure.
I think we missed how you generate the profile when you're on SSH only. You said par cluster, but I think you wanted to say they should call config cluster, right?
Oh, I'm sorry. Thanks, Thomas. Yes, I'm sorry. That's my bad. It's a config cluster. Yep, thank you. That's Thomas from MathWorks as well. So thanks, Thomas. Appreciate pointing out. All right. So let me just bring it back. Walk everyone through what we did to this point. We went to the parallel menu item. We clicked Discover Clusters. It brought up a dialog box. It searched the network for a configuration that we created that describes Carolina. We selected the Carolina profile, and we've also, for the moment at least, made it to be our default profile. And now we should see when we go to the parallel menu item that Carolina has been added and it's been the default. Okay, so that now it's either that or calling config cluster, and config cluster is only if you're doing this from the command prompt. You're going to call C equals par cluster You may not see this message here. This message is only displayed once per MATLAB session. So if you don't see it, we should still act on this. So we're going to set the additional property project name to be the one that we're all using today. And then the last step is that we're going to add the reservation. Okay. All right. So hopefully we're all caught up at this point. Let me catch up myself. All right. This might not actually. Oh, okay, good. All right. So the reason that I'm saving this profile is because if I quit MATLAB, I want to retain those properties values. I mean, technically you don't have to, but it would certainly seem to make sense, right? So we'll save the profile. So that's being stored now for us for future use. And now we are ready to create our Carolina pool. So pool equals C dot par pool. And in this case now, I will type the number 40, okay? So this is, okay. Let me try something and then I'll confirm. Okay, I believe that should work fine. So what I'm going to ask you to do is set the following. So we're going to set the additional property of mem per CPU, and we're going to set it to be the empty string. Put a semicolon at the end of it, and then save that profile. Okay. So I'll right. Okay. So let's see. There we are. And I'm going to just do this separately. No one should do this. All right, good. So here we can see that people are okay, good. All right, so some jobs are getting submitted to the cluster. All right, good. Okay, thumbs up if you're able to submit and get a Carolina cluster run or pool run. Yep, good. You'll know because the MATLAB prompt comes back. So when you start the pool, MATLAB will display some of the parameters that we passed on to the job, onto the scheduler. This is a clear distinction from running a local pool where we don't need to specify any of these. But the MATLAB prompt will stay hung until the job has been, those 40 workers are launched. And now we have the MATLAB prompt or the chevron that's come back. So, okay. Did anyone else have an issue? Well, yeah, did anyone have an issue getting their pool running? Let's see how, still waiting. Okay. Yeah. And I do want to make sure that for anyone that's waiting, it's important that you used the reservation because the reservation is what allows you to sort of hop the queue to this point. So all these job 1, 2, 6, 2, okay, these are all folks that are, well, it looks like there's a couple of folks are non-zero exit code. Okay, so we'll certainly need to look at it. What I'm going to do, today's workshop is about showing several modes. I'm going to, we'll have some live demonstrations, but at some point it gets more into like a lecture format and it's just slides and so forth. So either at the break or certainly at the end of today, if anyone had any issues getting jobs running, let me know and we'll get it resolved, because that is the point of the workshop. Sorry, so let me. But what I wanted to say to that point is that, just to set expectations here, this is a shared resource, right? So even after today, if you were to get things up and running, in fairly quick order, tomorrow when you go to submit your job, honestly, it could take the better part of the day to start up a parallel pool. This is one of the reasons or the advantages of batch. With batch, you just submit the job, and maybe it might run later today, finish in a couple of days, but you don't need MATLAB to continuously run. Par pool requires that the MATLAB client is always running. So in order for you to do anything, you have to first wait for these workers to start up, and then you can run your code. So I'll talk more about batch in a moment. All right, now that hopefully the pool is up and running, what can we do with it? Well, let's go back to our previous example. So we're going to run. Actually, I think I did that right. Okay. All right. So I ran 8 iterations and it ran in 3 seconds. So this might not be a terribly good example, right? I mean, I've got 80 workers, right? So this is an example where think about the number of iterations that you want, work around that. So instead of 80 iterations, what if I run 80 iterations? I mean, 8, I run 80, right? So this should also take 3 seconds to run, because now this is all getting doled out. I beg your pardon. I'm running 40 workers. I'm sorry. Yep. And then, so let's increase this, right? So now instead of 80, let's do 160, right? So this takes about 12 seconds to run, okay? So you get a sense that where you could run things, a smaller number of iterations, a smaller data set this morning, because you have less resources. Now that you have access to hundreds, if not thousands of cores, you really can start doing a lot more with Carolina and so forth. So anyone been able to run something on this order, 10, 12 seconds or no? Yep, thumbs up. No. Is it, so did that pool start? The pool started? All right. So let's jump to slides here. And okay, so the important thing to understand here on this slide is that MATLAB is going to generate a script for you. So we are launching MATLAB one way or another. Right now, we're using Carolina and we're logging into login node, and then from there on compute node. So MATLAB's running, and then it itself is also going to then generate a Slurm job script for you, right? All right, so this was the example or something similar that we just ran a second ago. Notice that, in this case here, we ran 4 workers, and locally we ran 64 on the cluster. They both took 60 seconds. It's because in one case, we're only running 80 iterations, and the other 1,280 iterations, right? So in this case, we can't run pause of 3 any faster, but we can run more iterations in the same period of time. All right. I've sort of hinted at this already. We've got 64 workers that are running. I can run in that period of time 80 iterations or 100 iterations all in 6 seconds, right? Because it really comes down to being modulo 64. So you want to think of the number of workers that you start to be, some factor of how many iterations that you want to, right? There would be no point. I could run 120 iterations in the same 6 seconds and so forth. So, okay. So then it's like, well, this is kind of cool, right? Like, how big can I start making this, right? Like, what are we talking about? And just to give you an idea, I mean, here's 512 workers, right? Now, this is probably without a reservation. I don't think I had a reservation at the time. Realistically, 512, that's 2 nodes. At least 2 nodes. But when I ran this, it took about almost 4 minutes for the job to start up. The job here is submitting the job, all 512 workers starting up, connecting, and so forth. But in 3 or 4 minutes, I've got access to 500 cores, 500 workers, and I'm running, the same toy example. I'm running 10,000 iterations all in a minute. And that would have taken me 8.5 hours to run this same code serially, right? So there's really a lot of potential here. Notice that on this slide here, what I did was I just let it sleep for 30 minutes. And this is what you will see. If you just walk away, at some point, your local pool will shut down. That's a difference between batch. Batch, when the job finishes, that's it. It ends immediately. With an interactive pool, that will continue to run. This is something you want to be mindful on Carolina. You don't want instances running unnecessarily. All right, so let's jump to the workshop examples. I'm going to ask everyone to go to MATLAB and then just run the following two commands, all right? So we've already downloaded these files. So let's cd. So I'm going to cd to user path. And then I'm going to cd to MATLAB parallel workshop, and then part 2. All right. So in here are a collection of files that we're not going to use all these files, but certainly this has all the files that we will need. The example that we're going to go through is estimating pi, right? And the way that we're going to do that is we're going to integrate from 0 to 1 over this curve, right? And there are a couple ways that we could solve this problem. I'm going to show you how to write this using a parallel for loop, and then I'll show you how we can do this using a new parallel construct called SPMD, right? All right, so if you think about it, what we need to do is we need to take the integral for each one of these segments and then add them all up, right? So that's a good example of parallelization. It doesn't matter if we take the integral here, then here, then here, then here, we're still going to get the same estimation at the end of it. So what does a parallel for loop example look like? In this code, I'm going to get a handle to my pool, and in there will tell me the number of workers that are associated with that pool, and that's what I'm going to use to break up my curve, right? So I'll have if I have 4 workers, it will be divided into quarters. If I had 8 workers, it will be divided into eighths, etc. So I need to calculate for my integral. I need a lower bound and upper bound. So I'm going to linearly space from 0 to 1 the number of segments. That's the number of workers plus 1. That's because one person's lower bound is another person's upper bound. So we have 1, 2, 3, 4, 5, right? So if there are 4 workers, we need 5 values. And then we're going to run for I equals 1 to the number of workers. A is going to be the lower bound, B is going to be the upper bound. And then we'll take the integral of our equation. And notice again, we're using a function pointer because we don't want to call quad pi right now. We want to delay that until a later time. And then we pass in A and B. Now, each worker is going to have their own version of A and B, right? So for worker 1, A is 0 and B is 1/4. For worker 3, A is 1/2 and B is 3/4, right? But they're all running at the same time. Okay, so we're only running the number of iterations equals the number of workers, right? All right. So we'll take the integral, the local integral, and now once we're finished with the parallel for loop, now we're going to sum all of our integrals together. And the reason that we were able to operate on my integral is because my integral uses the loop variable idx to store all the values. Remember, we saw that with the par feval example, right? Where y equal, and we couldn't bring y back because what was y? Here we have an array of integrals, and now we're summing them all up together. And then we're simply going to finish this off by printing out what MATLAB says pi is, what's our approximate value that we just calculated, and then let's just look at the difference between the two. So we do have another parallel construct called SPMD. It serves an entirely different purpose, but I'll just highlight it briefly here. So par 4 is for speeding up your for loops SPMD is for working with large data or distributed arrays scattered across multiple nodes. And this is where my distributed array will be segmented across n number of MATLABs, and each MATLAB is on a different node. We stitch all the data together, and then we operate on that distributed array as if it were local in my in memory, but in fact, it's actually distributed across multiple nodes. And this SPMD, which is single program multiple data, we don't actually use any distributed arrays, but it does show that we could assign A to be SPMD index is the rank. So here, this would be, for instance, worker 1 minus 1 is 0 divided by the SPMD size, which is the number of workers, is 4. And then B is 1 over quarter. So all this code is being run on each one of the workers separately. And then we integrate, we add all the values together and so forth. So this is more for a leave behind. You can take a look at it more at another time. All right. So when we go to run the code, we can see that locally 4 workers start up. And then when we calculate or estimate pi, we get something that's close but not identical. And maybe if we had more workers, then when we calculate our integral, we'll have less of an error between each one. And so we would expect that the error would be much smaller, if not 0. So how do we do that? We're going to start it. We close our pool, and then we start our Carolina pool. And here we're going to use 64 workers. And because each worker is doing much less, the error or the step size is much smaller, and so we get, in fact, an error of 0. Now, there's a trade-off here, right? On one hand, I can start up maybe a local pool of 4 workers and can start up pretty quickly, but my error might be outside my tolerance, or I can spend more time waiting for more resources to be available, and then get access to significantly more workers and get improved performance. So it really is your own choice. All right, let me just. Okay, I'll tell you what. We're gonna talk about GPUs, and then this will be a good point for our break. So Carolina does have access to GPUs. How many have access to GPUs on your own desktop engineering machines? 1, 1.5. So maybe it begs the question, which GPU, right? I mean, we all probably have some GPU on our machine. So specifically NVIDIA GPU machines, right? So not AMD or Intel, et cetera. So MATLAB supports NVIDIA GPUs, and those are on the cluster. I'm going to just go through a couple more screenshots here of showing you how you could request a GPU. So I mentioned that when you call salloc, right? So this is how do we get onto a compute node? There's a lot of things that we can ask for. And one of them is whether or not we want any GPUs. Again, refer to the Carolina Slurm documentation for more information. But here what we're doing is we're specifying the number of GPUs we want is 1. And then in addition to that, there's a -P, and -P stands for partition. So what the folks have done is pretty common, is that we've taken this cluster and we've created these partitions or these condominiums where each subcluster represents a different, common characteristics between the different nodes. So one set of nodes might have more or less cores, more or less memory. In this case, anything associated with a Q GPU partition has a GPU on there. What you're asking for now is, okay, I've got a machine that has a GPU. How many GPUs do you want? And Mate, correct me if I'm wrong, there are 8 GPUs per node. That's pretty cool, right? So here it's saying I want 1 GPU. And that's important because actually, unlike asking for non-GPU nodes, where you get the entire node, when you ask for a GPU machine, you get actually a portion of that machine based on the number of GPUs on your machine that you requested. So if you ask for 1 GPU, you get 1/8 of that machine, versus if you were to ask for 4, you get half of that machine. All right. So other than that, it's similar in how you were requesting the node. You're going to specify the in your allocation the project name, X11 for because we want to run MATLAB graphically, and then the number of GPUs and the partition.
Have you also specified this new style of this? Have we to write this one? No, now.
I apologize. I couldn't hear everything. Do I also need to specify one more time, please?
Have we specify this new command that you type it in terminal also? No. I just asked about this participant. We have to type the same things also.
No. Oh, I apologize. No, we're not gonna run this. I'm just gonna go through 2 GPU examples on the screen. So sorry.
Okay.
Yep. Okay. All right. So one of the commands that we can run in MATLAB is called the GPU device command, and this tells us something about the characteristics of the GPU that you have access to. And there's a very important one here, which happens to be the amount of memory, right? So this has about 45 gigs of memory. And that's a really important statistic because the nodes that you have typically have access to, I think it was a third or a quarter terabyte of memory. GPUs can be very fast. There's thousands of threads on a GPU device, but it doesn't have nearly the amount of memory. And we're going to see that in the second example. All right. So what I'm doing here is I'm calculating or running a fractal example. Specifically, this is a Mandelbrot that we're running. What I want to point out is that MATLAB has overloaded over 1,000 MATLAB functions that know how to operate on a GPU array. GPU array is perhaps a new data type for some of you, similar to a numeric array that is storing that memory on the local memory of your machine. A GPU array stores the memory or the variable on the GPU itself. Okay, but because MATLAB has overloaded 1,000 MATLAB functions, you'll notice that in the code below, there's nothing in here that says, well, if I'm on a GPU, run this version of Mesh Grid versus a non-GPU version. So Mesh Grid, complex ones, all the matrix math, all of this is overloaded to support GPUs, right? So the way that this is being created then is I'm going to pass in the type that I want to run it on. This is just a demo. Typically, you would not say, well, pass in GPU or double. You would just simply, no, I want to run on a GPU. And you would just say, okay, create a GPU array. But once X and Y have been created, then MATLAB knows how to do everything with the GPU. All right, so how do we call this code? We're going to run calc Mandelbrot, and we're going to specify whether we want to run it on the CPU or the GPU. We're going to wait for that to finish running, and then we're going to plot our results, and then we're going to plot the amount of time it took to run on the CPU and the GPU. Notice one of the things that we did here is we specified the number of computational threads. So this morning when we ran maximum comp threads, it came back with the number 4 or what have you. When we submit, and we'll see this more with the batch command, when we submit jobs to the cluster, by default, MATLAB only allocates a single core to run MATLAB. So I'll show you the impact of downsizing the number of threads allocated to our FFT in a second. All right, so when we run the Mandelbrot example, it takes 36 seconds to run on the CPU, and we can see on the GPU, it takes less than 1 second to run. That's pretty good performance improvements right there, right? Now, this doesn't require a parallel pool. The only reason that you need a pool is if you want to run a collection of workers or a parallel for loop and run across multiple GPUs. All we're doing in this example is running on one GPU, right? So if we had not specified that the number of computational threads was 16, and if we defaulted to 1, we can see that it takes over 4 minutes, 5 minutes to run on a CPU with only 1 core dedicated to it. Okay, so you look at this and say, well, this is fantastic. I'm going to take all my code and convert it to a GPU. Well, as I mentioned, the GPUs only have a certain amount of memory. So in this last example, before our break, I'm going to show you what happens when we ask for too much. In here, I'm going to pass in the size of the matrix that I want to call or create a random matrix of, and then I'm going to take TikTok and run it against, or I'm going to time how long it takes to calculate the FFT of my matrix, okay? All right. So the FFT of my matrix. Now I'm going to run a second tick tock right here. So T naught is being timed here, and then we'll see how long it takes to take our CPU matrix, cast it down to a GPU array. I'm going to calculate how long it takes to calculate the FFT of the matrix, of the GPU matrix. I got to pull the results back from the GPU onto my machine, so maybe I can plot it or whatever, and then we'll stop the timer. The last timer that I want to run actually is right here. I just want to see how long it takes just to calculate the FFT on a GPU, right? So the first time I run this, I'm going to first clear my GPU device, and then I'm going to pass in, I'm going to see that it has 39 gigs of memory available. So 2 to the 16th is, I believe it's 16 gigs. So this should certainly fit in memory. But we noticed that although the CPU has no problem running this in 32 seconds, that the GPU runs out of memory, right? So even though this 2 to the 16th might be 2 to the 16th times 2 to the 16th times 8 for a double, it might be significantly less than the 39. There's a lot of temporary variables that we have to create and so forth. So you have to account for that. So let's downsize our matrix down to 8 gigabytes. And here we'll notice that on the CPU, now it ran for a second. Now we're 2 to the 15th. So it took about 2 seconds to run. The GPU calculated in 2 orders of magnitude faster, but notice that the total time was about the same time as it took to run the CPU. So the total time is how much time it took to take the matrix, send it down to the GPU, run it on the GPU, and bring the data back, right? And so, if you think about it, of that 2.82, the vast majority of it was just the communication back and forth to the GPU, right? Because here we can see it's not even 0.8, it's 0.08, right? So the FFT was about 24 times faster on the GPU than the CPU. But if you include all the overhead, it took almost about the same amount of time. So what does this tell us? It means that if you're going to use the GPU, first of all, you have to be mindful of the amount of memory you really need. And the second thing is that you want to give it as much work as possible, right? This is a really simple example. We spent more time sending data back and forth than it took to actually run the code. So you don't want a context switch where you're sending data to the GPU, sending it back, doing something, send it back, maybe bring it back, plot it, etc. Give each GPU as much work to do as you can. All right. So with that, I want to take a break. I know I've thrown a lot at you. When we get back, we're going to pivot away from parpool, and we're going to talk about batch, which I really think is going to be a great feature to use, and you'll see and understand the value that batch has. So I got just before the bottom of the hour. Let's come back at 2:45. So, okay, thanks. Well, welcome back. We're on the home stretch here. Here's the last segment of the afternoon. To this point, we've been talking about parpool. And there are certainly values to parpool, being able to run your job interactively, or you have this interactive session, right? We start the pool, we run a parallel for loop, et cetera. What we know is that the parpool may take a little time to start up because you're requesting these resources. What we know is we can only have one parallel pool running at a time. And we can only have one par 4 running at a time. So we can't have nested par 4s, but we can have serial par 4s. So we can have one par 4 running and then another and another and so forth. But what if we want to have multiple things running at the same time and also having access to MATLAB to do our own whatever work, right? So that's one possibility. What if we want to simply take the code and launch it onto the cluster and then walk away, right? We're doing some field study and it's going to take a week to run our models, right? We have no interest in running MATLAB all that time. So the batch command provides the ability to run an asynchronous job. Asynchronous means that it's not blocking MATLAB. We submit the job to the cluster via MATLAB, okay? Now, I should also say that as I'm describing this, some of you who are familiar with HPC, Slurm, schedulers, et cetera, may start to already hear, well, wait a minute, I can do this. I can write my own Slurm script. Why do I need MATLAB to do this? And hopefully it will be obvious at the end of this. Okay, so the way that we're going to do this is we're going to get a handle to our cluster object using C equals par cluster or CC. Sometimes people don't like to use single variables for their single names for their variables. So, but anyway, and now what we're going to do is we're going to tell the batch command, right? So job equals c dot batch. We're going to pass in where the function that we want to call and the number of outputs, and then a cell array of input argument lists. So this is, although there's a lot of similarities with the par feval command, batch can do a little bit more than what par feval can do. And so therefore, we can't just have a comma separated list of input arguments. There's actually more arguments that we can pass to batch. So for that reason, we're going to use a cell array to pass in all the input arguments to our function. So first of all, what are we trying to do here? What I'm interested in knowing is where, when we submit a job to the cluster, is MATLAB running? And the reason this is important is because when my code is running and I want to read files from disk, or when I want to write files to disk, it's important to understand where is MATLAB running at that time, right? Okay, so let's start off with our sort of first hello world example. Let me jump over to, okay. Notice that prior to the break and then leading through the break, because I hadn't been running anything on the parallel pool, that the Carolina pool had expired, and that shut down my Slurm job, okay? But, shutting down your pool does not quit MATLAB. All right, so I'm going to clear my screen. And the first thing is I'm going to just type PWD. PWD is print the working directory. And this tells me where MATLAB is currently running. And I'm curious that if I were to submit a job, where does MATLAB run at that time? So let me ask, who has a thought of, like, when I'm calling the batch command, it's going to run the job on some node, some other node on the cluster. Where is the MATLAB process running, right? There's probably a couple of good options, right? Where do you think MATLAB is running these workers when I submit a job? So what's one possibility? Cores? Not core, but like location, like where could MATLAB, so MATLAB could be running in the same directory. The workers could be running in the same directory where the MATLAB client is running, right? That's one possibility. Another possibility is it could be running in your home directory, right? So this is a pretty simple example, but it's actually a very important one because, again, you need to know where MATLAB is running on the cluster. So as it turns out, when we submit the job to the cluster, it will be running in the same location where the MATLAB client is running. And that's configurable. We can specify where it will run on the cluster because maybe I've got all my data files in a different directory. So we can specify that. But let's go ahead and submit our first batch job. Right? So I've got, so C equals par cluster, and so there it is. So we have a handle to our cluster object. And now let's go and submit a job. So at PWD, and then the number one, because this only has one output argument, and then PWD does not have any input arguments. So you're going to just type in the empty cell array, and then we'll hit enter. Now, just like par pool goes off and generates a job for you, but it's an interactive job and it won't come back until that pool is running. Batch also is submitting a job for you, but one of the things you'll notice is that that prompt should come back immediately, right? It's an asynchronous command. It just, all it's responsible for doing is submitting the job to the cluster, but it doesn't have to wait for it to run and finish and so forth. On the flip side, we don't really know anything about the state of this job. All we know is that we've launched the job. Okay, so let's take a look at, let's go look at what jobs are running now. Okay, good. So we can see a bunch of jobs are starting to get submitted here. Okay, so good. So now that the job has been submitted, I need to know something about the state of that job. And the way that we can do that is by typing job.state, and state is capitalized, capital S. And there are at least 3 states of a job. There's queued, there's running, finished, and failed. Okay. So in this case here, MATLAB has submitted the job to the cluster, and it's come back and it's told us that the state of the job is finished. Now, again, this has a lot to do with the fact that we're using this special reservation that helps expedite starting the job. So thumbs up if everyone's got into the finished state at this point now. Thumbs up. Yep, good. All right, nice. All right, so we're 2/3 of the way there. We submitted the job. We got the state of the job. But we need to get the results of running that job. And the way that we're going to do that is we're going to type job.fetchOutputs, and it's camel-cased. So all lowercase letters except for the O is capitalized. And what we want to do is specify which output argument we want. Now, in this case, we said that there is only one output argument. So we could do, for instance, curly brace 1, the first output argument, as a sort of as a habit. I just always say give me all the output arguments, but it will be the same. And when you run this code, your directory might be a little different, or your output might be a little different, but it should actually be in the same directory that the MATLAB client is running. Now, again, we can pass in an additional argument to batch that dictates where the job should run on the cluster, but for the time being, this will suffice. So everyone got something like this. They were able to fetch the results. Okay, good. All right, so there we are. Now, you don't have to do the following, but start thinking about this, right? So if I said c.batch, and then I'm going to call some random matrix. It has one output argument. Maybe it has right. So here we go here and there and there. Okay. So it might be a bit hard to appreciate what we've just done here, but it's going to hopefully make it clear why there's a lot of value in this. We just submitted 3 jobs from MATLAB. Okay. For those who are familiar with Carolina, with Slurm, and so forth, think about what you might have to have done to submit 3 jobs at the terminal window. Now, yes, you can use job arrays, but sometimes your jobs aren't related, and what have you, right? So here, I've just gone off and I've launched 3 jobs. But the other thing is that I've done it from within the MATLAB environment. Okay. And what that means is that when the job is finished, now I can do something with it, right? So again, if you were to write this in your own, writing Slurm, what would you do? You'd have the results written somewhere, but when this job has finished running, let's see if it's finished. Okay, good. So now we'll say y equals job.fetch outputs, and I'm going to get all the results, and then I'm going to plot y. Okay, so the reason that I'm showing you this is because I'm a firm believer that when you're running jobs on a cluster, that the compute is half of the story. Okay, you want to run your models, but then what are you going to do once you're done running your models? Now I want to take this, I'm going to embed this into a live script, I'm going to generate a PDF, and then I'm going to publish my paper. And you can do all of this contained within the MATLAB environment. And that, I think, is what's powerful about this. You can use Parpool and you can do some of these things, that's fine, but it may take days to run the code. I can write my own Slurm SBatch script, but it's very discrete steps. If instead you run MATLAB through VNC session or OD, whatever the case is, and you can run MATLAB this, I'm not suggesting that you run MATLAB interactively. What I'm suggesting is that you launch your Slurm jobs via MATLAB, and then once the job is finished, you pull the results in and you can do your post-processing all here on Carolina or whatever, right? So, and I would also say that once you start getting used to the batch command, For those who are in your questionnaire at the end of this, if you specify that you're interested in remote submission, batch is really the only thing that you can do. You can't run interactive pool sessions from your machine onto Carolina. You can only use the MATLAB batch command. So, okay. All right, good. So where are we? So we know that we can use the batch command then to submit one or more jobs. And I'll show you how you can customize those jobs in a moment. We can get the state of the job. Now, all of this is being done while MATLAB is running, but I'm going to show you in a few slides how you could quit MATLAB and be notified that the job has finished running and how you can get the results at a later time. So you don't need to keep the MATLAB client running to fetch the results. But in this case here, the state is finished, and it only makes sense to fetch the results once the job is in a finished state. So, all right. So running PWD doesn't require a pool of processes, right? So let's now layer on top of this. If my code does call PARP4, SPMD, et cetera, how am I going to request a pool of processes? And so we know that we can certainly explicitly call PARP pool. So if we take a look at this example, who has a thought or suggestion as to when or where you would start your pool, right? So let's look at the code. For I equals 1 to 8, we're going to assign A of I equal to rand, right? It's about as simple as it gets. But in order to run this code, we need a parallel pool. We know that MATLAB will start one for us, so that is an option. But when we submit a batch job, you have to explicitly specify your pool. Batch, by default, will only provide you a single core, right? So it doesn't go through and look at your code. We have no idea how many workers you need. And on Carolina, we wouldn't know if you need 100 cores or 10,000 cores, right? So let's say, for the sake of discussion, that we have to tell MATLAB the size of the pool. So it probably makes sense just to embed it right here, right? Let's just call par pool of 4, right? So we run the code par pool of 4, we spin it up, and then we assign A of I dx. Okay, so I look at the code and I said, well, that's fine. Everything works well, but I want to tweak it, and I want to change the number of iterations from 8 to 80, okay? I then want to go rerun the code. What's going to happen? Is this going to run successfully if I run this code? Second time through. Well, think about the state of your environment, right? Just because you finish running the code doesn't mean that the pool dies, right? We already know that the pool will die on its own after 30 minutes of idleness. So if we were to go and run this code a second time as it is, we know that we can only have one parallel pool running at a time. So MATLAB says, well, okay, the first thing you've asked me to do is start a pool. Stop. I already have one that's running. Now, there are defensive ways that we could write around this. So let me not go into those, but there are things that we could do. But really, I think the best thing is to not embed calls to par pool directly in your MATLAB code. Keep those things separate. Okay. So then the question is, okay, if that's the case, then how, when we submit a batch job, if we can't call par pool within our code, then how do we specify, or how do we request a pool? And you probably saw that in the call to batch, we can specify a pool size, okay? All right, so let's take our calc_pi example, okay? So I'd like everyone to, let's get a handle to our, close this. So if you don't already have it, so C equals par cluster of Carolina. And then we're going to submit our job, calc_pi. And in this case, there are no input arguments. But we'll specify a pool size of 8, right? So we're going to calculate, we're going to run our integral across 8 workers. All right. So we've, if you don't specify a pool size, then you're only going to get a single worker, and that single worker will run both your serial and parallel code. So if your parallel, if your code has, you know, par 4 I equals 1 to 1,000,000, but you don't have a pool running, then that single worker is going to run that code as well. It will run the for loop in reverse order, actually. So here's my question. We have a pool size of 8, and yet the number of tasks is 9. Now, this is some Slurm syntax, and maybe you don't know a lot about Slurm, but you can certainly look at this and say, well, I get the impression that 9 workers are starting up. Who could explain to me why that makes any sense, right? If I want a pool of 8, why did we get 9 tasks? Think about the serial and parallel code, right? Sometimes we're doing some serial code and then we run the par 4 and then some other serial code, right? And so we need something to orchestrate all that. And so we always add one additional worker to the pool. So I will tell you that on Carolina, there are 128 cores per node. If you're going to run across multiple nodes, I would do it in a modulo of 128 minus 1. So I might say like 3 times 128 minus 1, because if you ask simply for 128, 512, et cetera, you're going to actually get plus 1, and it will give you 1 extra node, and you own the entire node. So I would keep this to be just under 120 or multiples of 128. Okay, so we go to submit the job and we see that it's finished. And when we go to fetch the results, nothing comes back, which doesn't make an awful lot of sense, because MATLAB tells us that Slurm tells us that the state of the job is finished. And yet when we went to go to fetch the results, nothing came back. And the reason is because when we look at our batch command, we told MATLAB that there are 0 outputs getting returned. Even if your code is a function that has 4 or 5 or 8 output arguments, we don't know that that's what you want returned. And there are good reasons not to return all of that back. So you have to explicitly tell us how many are getting returned. In this example, there were no return output arguments, so nothing gets returned. So let's take a sidestep for a moment and talk about how do we get data returned back from calling our function. There's probably at least 3 ways that I can think of. The first is that your function may return n number of output arguments, okay? The second is that your code might produce some diary, and we looked at that earlier this morning with the par feval, right? So we looked at the futures diary, right? And then maybe your code also saves some files to disk. So let's look at each one of this. Here we have another example, test_FCN. And we're going to, again, interweave serial with parallel and then serial code again. We'll display that we're going to start our simulation, we pre-allocate A, and then we have a tick tock around our parallel for loop. A of IDX equals some value. We're going to pause for half a second. We're going to display our loop variable, and then that's it. And then the last thing that we'll do, we'll write our A matrix to a mat file called results. We submit our job. Now, you know, if I'm going to have 300, the number of simulations I want to run is getting passed in. So here, that's 300 simulations. The pool size is 10, right? Now, again, you don't have to, the input argument list doesn't have to include the number of iterations that you want. That's just how I've written the code. Typically, your code would hard code how many iterations, or maybe you're looking at your folder and saying for I equals 1 to number of files in my directory, or whatever the case is, right? It's rare that you would pass in how many sims that you want to run. So when we go and once the job is finished, once we finish and we fetch the results, 300 simulations, it's pauses per half a second. So it's 150 seconds. 150 seconds divided by 10 workers is 15 seconds, right? So this makes sense. But what we didn't get back was A. And again, that's because when we told MATLAB how many output arguments to return, we only asked for the first one. If your output argument list, if you have 4 or 5 and you want the third one, you need to get the first, second, and third one. So why would you only ask for a portion of the output? And it actually has more to do with remote submission. So a lot of data is going to get passed back and forth. And if you were to have jobs submitted remotely, you'd only want to have the minimum amount of data that's getting passed. So honestly, when I'm running jobs, more often than not, I'm looking at failures. I don't necessarily care about the things that passed. I care more about the things that failed. And so therefore, if a job failed, then I want to maybe look at some additional results. But if everything passed, then maybe I'm not so interested in getting those results and so forth. So, all right. So that's one way. One way is to fetch the results. The second is to look at the diary, right? And so when we saw the par eval, we could see that a diary was being collected that's saying, yes, we finished another task, or we received another piece of data, et cetera. So because there's no parallel debugger, the diary actually can be very useful when you're trying to step through and figure out why something did or did not work. So here we're seeing that we've started the simulation. So there it is. And then notice that actually what we're displaying is IDX right here. So here's the loop variable. And notice that it's happening in any order, right? And we already know this well enough now that parallel for loops will run in any order. I cut off the bottom. I'm not going to display everything, but in the bottom, we would have seen that the simulation has finished running. So when we go back to our calc example, the way that we're going to get the results is actually looking at the diary. So the diary shows us this was for, I think, was a 400 iterations, or no, it was for 8, a pool of 8. So here we can see that was enough to get us zero errors. So good. And then the last piece here is when files are being written to disk. So in this example here, we know that the matrix A is going to be stored in the results.mat file. My question to you is, where is results going to be written to? Where in the directory structure? Well, we certainly know it's not going to be written to your laptop, right? Everything is happening on the cluster. By default, MATLAB's going to just write to the current directory, wherever MATLAB's running. That's why we ran that example earlier, the PWD. It's helpful to understand, oh, okay, I see where MATLAB's being run. It's run in the current directory. We'll talk a little towards the very end. What if we run a collection of these jobs and they're all writing to the same directory? So how can we make this a little bit more error-proof and so forth? So, all right, I'm going to take a sidestep now and talk about threads. I talked a little about it in the past. When you're submitting batch jobs, by default, MATLAB is going to only assign a single core for each worker. Well, I said a worker is a headless MATLAB process. And so therefore, if your MATLAB client can use all 4 or 8 cores on your local machine, what would happen if you were to submit a job on the cluster and you only get 1 core to run your FFT, et cetera, right? So let's take a look in the following example. I'm going to pass in the size of the random matrix, and then we're just going to calculate the amount of time it takes to calculate the FFT of a matrix, right? So there's no explicit parallelization here. We're just using pure MATLAB with the math routines, right? All right, so I'm going to submit this twice. The first example is going to be the default way, pass in the size of the matrix. And notice that the number of CPUs per task is 1, okay? The number of cores per MATLAB is 1, right? Well, we don't have a pool size of 0. We don't have a pool size, so the default size is 0. 0 plus 1 is 1, so that's why there's 1 task, right? And it took 46 seconds to run that FFT on a 2 to the 16th by 2 to the 16th matrix. What I'm going to do now is I'm going to introduce a new concept of threads. And so we can tell MATLAB that the job should allocate 5 threads per worker. Now, again, there's only 1 worker, but notice that instead of 1 core per MATLAB, we now have 5 workers per MATLAB. And in fact, we get about, a 4 or 5 times speed improvement just by increasing the number of threads. So this is very important when you're submitting batch jobs, that you think about the code and how many threads it might be using. And you might ask, well, Raymond, I have no idea. I mean, on my machine, I've got 4 cores, but how do I even know if my code is even doing any threading, right? So if my code was to do IM read or you're reading from an image file. There's probably no threading there, right? So one thing that you could do actually is set the number of computational threads to 1, run your code, time it, and see how long, if your code takes 10 hours and then you specify the number of threads for your local machine to be, whatever, 4, and it goes from 10 hours down to, 5 hours, 6 hours, then you can tell that some of your code is actually multi-threaded. But if your code takes 10 hours to run with 1 thread and 10 hours to run with lots of threads, that tells you that there's no threading and we don't need to add threads here. But it's something that you have to think about because you will see a significant performance degradation. This is a good example of what you probably see on your local machine without even realizing it. MATLAB, when you start up, you get access to all the cores, right? So imagine that this is, you have on a 4-core machine, this probably would have taken like 12 or 13 seconds. You go to run it on the cluster, and without realizing, you see degradation, and this is why. So, all right. So, as I mentioned, both parpool and batch will submit jobs to the cluster, and there are times that you're going to need to tweak the parameters, such as the amount of wall time, the amount of memory, the number of GPUs, and so forth. So, if you look at the additional properties, you'll notice that there are actually a collection of things that you can specify. Probably, really, of all of these, one of the most interesting ones or helpful is getting email notification, especially with the batch job. So when you specify your email address, then when your job starts running, you'll be notified that the job started and you'll be notified that the job has finished running. This is fantastic because now you could submit lots of jobs, quit MATLAB, quit OOD, shut down your terminal session, and then you'll be emailed several days later when your job is finished. You don't have to keep monitoring. Now, I do have to show you how you can get results from jobs you ran days ago, but this way you don't have to keep MATLAB running all the time. The other ones are for much more, like if you know a lot more about how you want to configure your job. Things like constraints you'd have to know the different types of features that are on the cluster. Honestly, for GPU card and GPUs per node, I would just spin up an allocation on a GPU node and just run MATLAB that way. I probably would not submit, well, I don't know, maybe I'd submit a batch job, I'm not sure, but you can specify how many GPUs. The memory is only for GPU jobs. Because you own the entire node, there's no need to specify how much memory per worker. You own the entire node. It's only you only need to specify maybe the amount of memory if you're running on GPU machines. All right, let's keep moving. So the only thing that you need to do, and this is true whether parpool or the batch command, is you have to specify the project name. That's required, okay? All right, Simulink, I think there was a couple of Simulink users. I will just mention that just like we have support for running Simulink jobs interactively using parsim, we also have batch sim, and batch sim will spin up a pool of processes. So it's a somewhat similar argument list to batch. You can specify how many workers that you want to spin up. In this case here, we're modeling the heating system of a home, and we're doing that by creating a collection of temperatures. And then each worker is going to run through the model, setting the value of the temperature and so forth. So this is, again, for Simulink users. All right. What I want to do at this point now is start talking about ways that we can optimize your job, because you could spend a lot of time submitting your job or running your job in a less efficient manner. So here, what we're going to do is use scripts rather than functions. I'm sure, actually, as much as I think functions is probably the ideal way to write your MATLAB code, a lot of people sort of grow up writing scripts first. And so we'll take a look at the impact of using scripts over functions. In this case here, it's not, this is certainly not a traditional way of writing a script. I've just sort of embedded it all into one line. You could do this, but of course your script will be hundreds of lines of code. So you just pass in the name of the script you want to call, that's it. But here, we're going to create a variable X, and then we assign Z to be random of 3 by 3. The code that we're going to call is to create some temporary variable and assign it to be a 10 by 10 random matrix, and then assign Y equal to X. After I submit the job, I'm going to clear the variable Z. We notice that the only variables that are in our workspace are C, job, and X. When we get the state of the job, we can see that it's finished, and now we have a variable ants. So let's take a look at pulling the results back. When you when you run a script, there is no variables to fetch. There's no outputs to fetch because you have no output variables. So instead, we're just going to load. We're just going to load the job object, and that will load all the variables. And notice that when we do that, that we now have reintroduced the variable Z, which is odd because we cleared Z. So why is it that it's come back? And that's because when we submitted the job doesn't know what variables you need. So it takes everything in your base works or your college workspace or whatever it is, and passes it along with the job. And the same is true when coming back. We don't know what variables you need. In this example here, I'm using the variable temp to signify something that we don't really care about. But you'll notice that it comes back as well. So Z was passed with the job, and that's because we had this variable Z in our workspace, even though we never needed it in our script. Notice that the variable temp came back because we had created that when we were there. Now you look at this and you might say, well, okay, fine. So I've got a bunch of temporary variables, some variables in my base workspace that gets copied around and so forth. Notice the impact of creating these superfluous variables that are not necessary, but are still getting passed with the job, right? So this is just taking the time of how long it takes to submit this job, right? Not to run it, not to finish it, et cetera. It takes just under 2 seconds to run. When I create these random matrices, here, this is a 30 megabytes, 190 megabytes. We can see that it takes 3 seconds, 13 seconds, So maybe it's not a case where you have, a variable that's got, 100, 200 megabytes, but maybe you've got 5 or 10 variables and those collectively are, hundreds of megabytes, And also this is the overhead that you're going to incur every time you submit a job, and this is only exacerbated that if you did remote submission. It's even worse because now you got to copy all the variables from your machine to the cluster and so forth. All right. So when the job runs, today all the jobs are running quite quickly. They start quite quickly because we have a reservation, but we have a helper function will run that will tell you that if the job is queued, why it is. And so we're just querying the schedule for it. I mentioned that when you're using the batch command, a nice feature is to be able to get email notifications. So that way, when the job is finished, you'll get notified that it has. So the question then is okay, well, how do we get the results from running our jobs? And what we can do is go to the job monitor and take a look at all the jobs that we've run in the past. So if I come back over to MATLAB and then I click on the parallel menu item and then you go to monitor jobs, this will bring up a job monitor. There are different profiles. You want to specify, in this case, Carolina, and this will now go through and look at all the jobs that I've run up to this point. I'm going to let that fill up in a second. For yours, it's going to show you all the batch jobs you've run. It won't show you par pool because when you run a parallel pool, when you close the pool, it deletes the job and that's it. There's no artifacts that are left over. For batch jobs, because we want to be able to get that information days later, we always keep things around. So the job monitor, you can right click, you can look at jobs that had errors, look at the errors, you can get outputs and so forth. I'll show you towards the tail end how you can also tag your jobs so you can get better messages about what these jobs are. Because if you look at this, it's not very helpful to see that this is a batch job running a function, when in fact, these are all different types of jobs. So I'll show you how you can add a little bit more clarity there. But it is a good idea to delete your job after a period of time. So once the job has finished running and you no longer need the results, let me just see if it's, yeah, okay. Okay, so here's my job monitor. So we can see that I've submitted a handful of jobs over time. I have access to all of these jobs, but it also sometimes will take a little time to populate this if I don't clean up my jobs over a period of time. So I would suggest that you either right click on your job to delete it when you no longer need it. Or if you have a handle to your job, you can just type j.delete and that will delete your job as well. Once you delete the job, you no longer have access to it. So you want to make sure that you don't delete jobs that you'll need days later. But until you delete the jobs, you'll always have access to those data. All right. Let me just thing here. Okay. I'm sure everyone writes bug-free code and all the jobs always work and so forth. So bear with me. Imagine that you've written some code and it errors out. How do we start thinking about troubleshooting and so forth? Again, all of this is built around batch, not really parpool and so forth. So we submit the job, and we're going to submit actually 2 jobs here. One is, one's a function, and the other is if we're calling a script. And the way that we can get error messages from running our jobs is slightly different. So once a job has finished running, that's a function. When we get the state, we see that it's finished. But if we fetch the outputs, then that's when MATLAB will throw the error saying something has occurred. So just because it's in a finish doesn't necessarily mean that MATLAB didn't throw an error. It just means that the state of the job is finished. That's different than whether it ran successfully or not. For scripts, if we load the variables like we were doing earlier, that's when we would see error messages and so forth. We can get log files. So for those who are familiar with Slurm and know how to get error files or output files, MATLAB provides an interface to getting all this. So between the MATLAB error message, the Slurm log files, and then finally the Slurm job ID, we can collect all of this and create a help ticket and say, okay, here's my Slurm job ID, here's my MATLAB error message, here's my Slurm log file, and so forth. So, all right. I'm going to jump over all this because I really want to sort of get into the last piece for this afternoon, which is, right, I'll show you this, and then I'm going to show you how to write your own Slurm scripts, and then we'll call it for the day. Okay, so I mentioned that we do have the ability to tag our jobs. And the way that we're going to do that is that in here, I'm going to specify my email notification, and then I'm going to run 4 jobs, right? So I have a for loop. This is not a parallel for loop. This is just a regular for loop. I'm going to submit a bunch of batch jobs. And then what I'm going to do is after I submit the job, I'm going to specify that this is simulation 1, 2, 3, or 4, whatever, right? So you can tag your job after it's been submitted. And so that way you can get much more useful information. So, all right, let's talk about the third thing this afternoon, which is writing your own Slurm script. So just to review, in the afternoon, we talked about using parallel pool interactively, and we can do that for both a local pool as well as a Carolina pool. But the drawback is that we always have to have the MATLAB session running. Then we talked about the batch command, and the batch command allows us to spin up MATLAB and then launch a bunch of batch jobs, get emailed notification when the job finishes running, pull in the results at a later time, right? But it also requires, in both scenarios, that the MATLAB client is always running. What happens if we've written some MATLAB code and we just say, you know what, it's perfect, I know it works, I don't need to run MATLAB interactively, I just want to write my own Slurm script and submit a job. And that's the last piece that we're going to talk about now. All right, so we're going to take 2 of these. We're going to take both examples, and we're going to go back to calculating pi. And in the first, on the left side, we've got we're going to be creating a local pool, and on the right side, we're going to be creating a pool with Carolina. Now, earlier I mentioned that you should not make calls to parpool embedded within your MATLAB code. You should do that somewhere in your MATLAB session. But keep in mind, this is a completely autonomous MATLAB submission. This is everything that MATLAB is going to do. So in this case, we do need to start a parallel pool, and we're going to make that call in MATLAB, in our MATLAB code. But notice that other than instantiating our pool, whether it's a local pool, maybe just for across 100 nodes or whatever, or Carolina that we can run across multiple nodes. Everything else after that is identically the same, right? So all it is that we're segmenting this by maybe 4 workers, and this is segmented by 40 workers or 400 workers. But the code itself is identical, right? So we're going to submit both of these jobs. So the first job that we'll submit is just using a local pool across a single node. And to do this, we need to write a job script. Now, the job script is written using some text editor like VI or what have you, and it has to specify certain parameters for your Slurm script. In this case, we only have to specify 3 things. The first is the number of cores that we want dedicated to the machine. The second is that we have to add MATLAB to the path, right? We saw that earlier today. And then we have to run the code, in this case, MATLAB-batch, and then the MATLAB code that we want to run, which is CalcPy single node. So let's go ahead and let's do that. So we don't need MATLAB in this case. And I'm going to close this and this. And in fact, we don't even need any allocation onto a compute node. This is a really good example of what you would run on the head node, okay? So let me, let's clear everything up. I think, okay. All right, so I'd like everyone to just bring up a terminal window. And you're going to CD to /documents, and you should be able to hit the tab button. And then MATLAB tab, and then hit tab again. Tab one more time, and then you're going to make that part 2. So CD to /documents, MATLAB Parallel Workshop part 2. All right, so in here is 2 Slurm scripts, one for running it just across a single node and the other multiple nodes. Shubo, can you should have this in the Zoom list as well. Yep, that's right. Yep, thanks. Great. Great, thank you. All right, so Shubo has just pasted into the Zoom chat. So I'd like you to copy and paste what he's done. I'm going to run this, and then I'll. Shubo, can you double check? I might have left off the -A. Is it A or -A? Okay, all right, great. So here, let me. Okay. Sorry, folks. I apologize. What I've provided is not correct. So let me fix this. I will get this updated. I'll get the proper version sent out to you. I mean, you're certainly welcome to follow along. But all right, so I'm going to kill that, delete that, delete, and delete that. Okay. And then let me just MATLAB same thing here. Okay. All right. Let me submit the job, and let me explain what's happening. So, all right. When we were asking for when we want to allocate a compute node to run MATLAB interactively, we used the salloc. command. Here, we're using the sbatch command. So this is a Slurm batch submission utility. And we have to specify the project name. And then in this case, to help expedite it, we're specifying the reservation as well. And you'll notice that Slurm has come back with a job ID. Okay, so that way we can query the state of the job and so forth. And to do that, I can type SQ and then the name of the job ID, so 342241. And then F, the F is getting into the, oh, no, failed. Let's take a look. Yep. Mm-hmm. And let's rerun it. And let's job 45. Okay, so it's running. Okay, so this is this would be in the case where the code that I've written, you know, that calculating pi, I know it's never going to change. I don't need to run it interactively. I just need to run the job. It's going to write out some text file, and then maybe I'm going to do something with the text file, whatever. I don't need it perhaps in MATLAB, and I just want to launch my parallel job. Okay, let's check. Still running. Okay. What I'm also do then is let me submit my multi-node job. So this is very similar to yeah. Okay. Good. Similar to the single, but in this case now I need hundreds of cores, and so I'm going to use the Carolina profile. So let's take a look at 2, 2, 4, 5. And there we are. Okay, so notice that, and maybe this is, let me just bring this up here.
Raymond, could you share your Slurm script once more so we can change, the people can change their Slurm scripts, so make it run?
Okay. So what I did was I deleted everything other than setting tasks equal to 8. And then I changed MATLAB to be lowercase letters. So I'll let that sit for a second. Now, I'm going to go back to the MATLAB code in a moment, but one of the things that you'll notice in my MATLAB code is I don't actually hard code that I want 8 workers to run. I'm going to, I actually look up a Slurm environment variable that's being set by Slurm based on the number of CPUs per task. So when I submit my job, I specify how many cores I want, and then MATLAB uses that to dictate the size of the local pool that I'm running, okay? So notice that we're starting up a local pool with a pool of 8 workers, and there we are. We get good results. The reason that we have 8 workers is because we're starting up a local pool based on a variable size, and size is being calculated by asking Slurm, hey, how many tasks per node did you request? And that was being set by the number 8 right here, okay? You could certainly hard code in 8. If you knew that you're running 8 simulations and you only need a pool of 8, that's perfectly fine. You don't have to write your code this way, but you could. So, and then the last example is where we're running we are running our multi-node job. Now, notice that it's interesting, for a multi-node job, we're only asking for a single core. And that's because MATLAB is still going to generate a Slurm script, right? So all this is doing is launching MATLAB. When MATLAB calls par pool, it will also generate a Slurm job, and that will be 40 or 400 workers or whatever. So in this case here, you only ask for a single instance of MATLAB. When we run the MATLAB, submit the MATLAB job, we'll see that we have, this is the first job that's run, and then over time, here's 487, and then 488 is MATLAB submitting a job of its own. And then the output is that we've got we're using the Carolina profile to start up 40 workers. Okay. All right. Again, so this is certainly a way of doing it, right? You don't have to run MATLAB through OOD or whatever, but I find that, okay, now that the results are done, what am I doing next? And it's just a little bit easier if I would be able to submit a batch job rather than an SBatch script, and then just import the results into MATLAB and then do something with it. So. All right, we are on the home stretch. What I'd like everyone to do is to clear out their project name and reservation. Both of these are only for today. And when you use this next time, I don't want you to reference a project name or a reservation that's no longer valid. So let's go ahead and jump over to MATLAB. Let me get my allocation going again. So module load MATLAB. And all right, so we're going to type C equals par cluster. Carolina. And then we're going to unset the project name and unset the reservation. And then we're going to save our profile. And I'll leave that there for a moment for you to copy down. All right. So it goes without saying we covered a lot today. Truthfully, a lot of this is about awareness, right? What I'm trying to do is describe to you what's possible. You sort of have to figure out, okay, if I think about my code, do I need to speed it up? Am I running out of memory? Do I simply want to offload the code from my machine onto Carolina? If I'm going to run on Carolina, what are the different ways that I could do it? I could run an interactive pool. I could just use a local pool, and that's perfectly fine. Maybe I just need 40 or 50 cores, and I think that might be the easiest thing to do, just run a local pool of 50 workers, right? Another option is that I might need to have multiple cores, multiple nodes, because I want to run a 400 or 500 way job. And we saw that in a couple of minutes, I can get access to 500 cores and run my code, perhaps significantly faster. But, par pool requires that the pool is always running, MATLAB's always running, and so forth. It might take some time to start that up. So batch, right? We looked at the MATLAB batch command to be able to launch lots of different jobs, almost like par feval, right? So I can launch these processes while MATLAB's running, or I could submit my job just from within MATLAB, get email notification when the job is finished, and then log back in, do some post-processing and so forth. Or if I'm really hardcore and I'm just like, I know this code is bulletproof and I can just go in, not have any issues, I can write my own Slurm script and submit jobs without ever needing any allocation onto the cluster. Just log into login node and submit our jobs. So a lot was thrown at you today. I do want to thank the IT4I Innovation team. They've been very supportive and helpful through all of this. Thanks for all the MathWorks employees and Humasa for helping to staff the Zoom chat. As I mentioned, all of this will be collected. We will have audio and video recordings of this. We will have a Q&A document that highlights all the questions that you've asked. We'll get that posted. We'll post the PDF of both sets of slides. I would ask if you could, you'll be asked for a questionnaire. If you can provide any information about the course. If you'd like any additional support, first and foremost, I'd suggest getting in touch with the support team. They're an excellent resource. They certainly understand how all this works. We have local representation in the country, but also throughout Europe that can help. And with that, that's all I have to cover. So, Currently, if you want to, yep, it's all yours.
So thank you, Raymond, because this was an intensive day. And I think I can say for everyone that it was very interesting, inspiring, and hopefully we will have many new users on our infrastructure, the HPC infrastructure. So as Raymond said, Carolina and also Barbara are available for all Czech academia and scientists, researchers, but Carolina is also available to European-wide. I suppose online we still have some participants from other European countries. So Carolina is available also for you through the EuroHPC calls for resources. So thank you, Raymond. Thank you also to Shubo for helping with the chat, and for to our colleagues from Homosoft who have helped us to arrange this training. Thank you very much for coming. I hope you had a productive day and that you learned a lot and you will be able to use it in your work. And I hope to see you at some other courses. Thank you.